Good afternoon, and hello, everybody. I want to welcome you to the AI and Security webinar. This is an event co-organized with a number of European projects under the umbrella of European Power Force. We also have a project from the 6G SNS funded by Next Generation Services. And I'm very happy to bring you this event that will be basically hosted online. It will be also streamed by different platforms. The reason for organizing this is because there are a number of challenges that needs to be addressed since the transition from 6G to 5G, and nowadays with the 6G that is going to make the data in high throughput available to different ecosystems. So we are not only going to address the telecommunication domain, it is also very important to understand the data processing issues as well. So the webinar will be going to focus on the intersection of artificial intelligence and cybersecurity, not necessarily linked to telecommunications, but it will also nurture this effort for the next generation networks. As mentioned, we are going to cover these technologies that can help us to have more safer networks, more reliable and better protection of the actual data sets. Today we have a number of experts today with us that are going to discuss the latest research, the new technologies, and the solution to these challenges that can be to some extent addressed and using AI and machine learning in mobile networks. Thus, the webinar is going to treat mainly these three topics. The first one is privacy preserving AI, exploring the recent advancements and guaranteeing the data privacy for distributed AI, and also linked to novel concepts such as AI and encryption. Also, we are going to discuss about AI for network resilience, about using the artificial intelligence to predict network behavior, detect issues, but also to enhance the security in 6G networks. And the last session, not the least important, we're going to mix the AI with concepts such as distributed ledger technology for network management. So looking at how blockchain and AI can improve resource management and decision making in 6G. For today, we have a very interesting 11 presentation brought to you by different speakers. So we are going to have the part of the session after each presentation where we allow public to ask any questions. So I kindly ask you if you have something to wait for the presentation to be over, after which we are going to open the floor for questions. We will try to keep around 3 questions at the most to be on the schedule. So our first presenter is Professor Nineta Polemi. She is cybersecurity professor of University of Piraeus, and she's also CTO of Trustilio company. So I will give now floor to Professor Nineta. So Professor, can you please share your presentation?
Hello, everybody. Well, I didn't know I was the first one, but okay. Let me share my presentation. And first of all, thank you very much for this invitation. And my presentation today is actually more well-rounded. I will talk about some challenges and efforts that we examine and we see during these 2 projects that I'm involved. One is the FAITH project and the other is the CUSTODES project. We are dealing with and trying to implement and contribute towards building this risk management for AI systems, as mentioned in Article 9 of AI Act. Now, the question here is, of course, when they talk in Article 9 about the risk management, we talk about this iterative process that spans the entire life cycle of any AI system, but we try to assess the trustworthiness dimensions. And by the trustworthiness dimensions are actually well mentioned in Articles 10 to 15 in AI Act. So here we see that when we talk about risk management, we don't talk about only managing cybersecurity risks, but risks that actually impact all dimensions of trustworthiness: data governance, record keeping, transparency, accuracy, robustness, cybersecurity, etc. So this is a challenge actually to see how we can do that, and what type of standards we can use that already exist, but how we can enhance them. And this is an issue that this project FAITH deals with. And then about conformity assessment, Article 43 in AI Act mentions again that we need to assess and actually eventually be able to certify AI products. That's the hidden agenda behind this Article 43, and to assess the security and trustworthiness requirements of the AI systems. But now, how complex is this problem? How difficult is to develop a trustworthiness risk assessment methodology and tools eventually, and the conformity assessment methodologies? Well, we should also have in mind things are not as complex as they look. We should also always think of a digital infrastructure, information infrastructure that actually is it's a pyramid of interconnected layers. We have the infrastructural, physical layer, the telecom layer, the IT and AI layer, the services, and then the data that actually feed the services, and finally the users, whether they are physical users or smart objects. So actually, this is the usual digital information infrastructure that is hosted by any organization, whether it is, of course, distributed or not distributed. And so AI systems actually are in the third layer of any digital infrastructure. So as always, we wanted to secure all layers, all assets in this infrastructure. And now we don't only want to secure, but also we want to ensure the trustworthiness of the AI systems that lie in layer 3. So, well, actually, we need to follow the common cybersecurity practices, as we mentioned here, this framework with the NISA. And we need to start by securing and ensuring that the foundations of cybersecurity are there. So we need our infrastructure to be secure, as either have ISO 27001-005 certification on our infrastructure that hosts the AI systems. Then we need to find the additional threats that this AI system may have that we have not considered when we do a cybersecurity risk assessment. And finally, we need to consider which is the intended use and where and for which goal do we use this AI system, because then we may have some additional environmental threats that we need to consider. So when we talk about trustworthiness risk management, we should have in mind that let us think of layers. Let us not forget our basics. So for this trustworthiness risk management, as mentioned in Article 9, we need to consider what we knew in the past, apply NIS2, for example, or CRA or GDPR for privacy assessment, and integrate and implement privacy-related controls, cybersecurity-related controls, and then think about the additional threats that this or that we may have in these various trustworthiness dimensions and implement. So I remind you that when we talk about security, we say, you know, according to this ISO 27001, we have various dimensions: confidentiality, integrity, non-repudiation, authenticity, availability. So these are the dimensions actually we need to ensure that all assets in all layers of our digital infrastructure actually they meet this, we ensure these dimensions. Now for trustworthiness, we just go scale up. So for trustworthiness assessment, we need all the security assessment according to ISO 27000 series, and also we need to add the other dimensions, accuracy, robustness, and so on. So, but the way we think of it is we use again, the ISO 27001 mentality in 005, and just increase and enhance the threat landscape we need to deal with. And the threat landscape, we will consider threats for accuracy, for robustness, for transparency and fairness. The difference here is that the threats may not be only technical, they may be social, even socio-psychological threats, and we need to consider. And so, again, if a company, an organization has an ISMS that is designed to protect all dimensions of cybersecurity, in this ISMS, actually, we need this enhancement to think about how we will protect the trustworthiness of the AI systems in layer 3 in our digital infrastructure, and then it will be set. So think of an enhanced ISMS when we talk about to build an AI management, trustworthiness management system. And actually, the appropriate standard, the 42001, you see that is aligned with the 27001 because the mentality is the same. Of course, we do have some even the NVD, the National Vulnerability Database of NIST. Actually, we can find vulnerabilities there for AI systems these days, and they keep enhancing these AI vulnerabilities. Also, us with this AI exchange portal, we can find various threats for all these different dimensions for AI systems, technical threats though. Also, we see some initiatives that, for example, the AI risk repository that is hosted by MIT, and ENISA has an announcement that they will also build this European NVD. Let's see. So what we need to have in mind, and this is the way we consider this in the FAITH project, that what we need is an extended, let's say, security management process that actually will use and will consider threats from all other trustworthiness dimensions. And also this trustworthiness risk management needs to be considered in each phase of the life cycle of the AI system. But again, this is not something different. That's what we did for the security assessment as well. The minute something changed, we had to renew the risk management process. Same thing here. But here we are talking because the AI systems are very dynamic. We will consider clearly that the trustworthiness risk management needs to be per phase of the AI system. And I remind you, the AI life cycle consists of design, develop, and deployment phases. So for each phase, we need to activate a risk management. And the risk management, as I said, we use the ISO 27005 process that is business as usual. You need to identify your threats, but the threats for all dimensions now of trustworthiness, evaluate the threat level, evaluate the vulnerabilities that your AI assets have in this particular phase of assessment, and of course, these particular assets of the system under assessment. So evaluate your vulnerabilities, the vulnerability levels, the impact level, the impact that these threats may have to the trustworthiness dimensions. And of course, you can add to these impacts the business impacts of your organization and that is using this AI system for an intended use. So this iterative trustworthiness management process that we are building in Faith actually is based on 27005. And we added two more things. We consider the human oversight, as the AI Act talks about and mentions. And the way we consider the human element is first of all, we consider the maturity of the teams that deal and they participate in this particular life cycle that is being under assessment. What is the maturity of the team? And we have some psychological tests to do that. And also we consider optionally the sophistication of potential attackers. So if we have some knowledge about from the past, what do you expect that your potential attackers may be? Again, we calculate and evaluate the sophistication level. And these two more factors, the maturity level of the AI participants teams and the sophistication level of the attackers are parts of this usual risk calculation, which is threat level times vulnerability level times impact level, and again times the sophistication of the attacker and the maturity of the team. That's what we do in Faith. And here is another question that we are thinking lately. In order to consider the interaction and the connection of the AI's assets under assessment with different other assets, ICT assets and so on. So probably you can think about more technically, and we can think about how we can evaluate the technical trustworthiness vulnerability scoring. Shall we use the CVSS 3.1 or 4.0? And I remind you, of course, you all know that this CVSS is a standard way to measure severity of vulnerability. And the good thing about this standard is that we measure using also taking into account the environment of the asset that is being used. It's something that we need in the AI trustworthiness risk management. They consider the environmental metric group, and we can use that and how. So we have the by default measurement of the vulnerability using the base metric group. We have the time related. When do you are there any exploits for this vulnerability these days that would do the examination of the vulnerability, and also the environmental. So this is something we are looking lately of how we can use technical trustworthiness vulnerability scoring using CVSS. Also in CVSS, I remind you that they have two issues. They have these privileges requirements and user interaction, where there actually we can embed the sophistication experience of the attacker and of the defender. See, this is something again we play with of how we can embed this type of the human element within the CVSS. Of course, still this is not enough. It's not enough because trustworthiness risk assessment requires actually, as I said, many other dimensions, not only technical vulnerabilities, but also vulnerabilities of social vulnerabilities and so on. So it's not enough, but it's something to consider. Also, for conformity assessment of, as we said, the conformity assessment Article 43 requires eventually, that's what the Commission will ask eventually, to certify our AI systems. And of course, we need risk conformity assessment methodologies that do not exist. In CUSTODES, it's a project that we are dealing with automated certification processes and how we build a platform that actually vendors can use to develop their protection profiles. And in this case, it would be nice to use this platform for manufacturers to conduct risk management and build their trustworthiness protection profiles, because that's what we need in trustworthiness certification. And actually, they can the auditors can use a trustworthiness scheme that does not exist at this point, but they can use this platform to conduct and assess the protection, the trustworthiness requirements that will eventually be mentioned in the trustworthiness protection profile. It's a big challenge, and we have standards. We can use various standards. Standards are available. The question is how we can extend and how we can implement them in this problem. And the problem is, of course, they are not. We don't have a scheme for AI trustworthiness, and we don't have actually. ENISA has published this European cybersecurity certification scheme, but this is for cybersecurity certification. Of course, all components are there and we can use for trustworthiness certification, but this is something we need to really work on. The standards are there, as I said, 17065, 67, 15408, common criteria, 18045. We do have the elements, but the question is how we can implement to really build a trustworthiness scheme for AI system, and how we can assess. CUSTODES is a project, actually, as I said, that we are working on these issues. And another very big problem, of course, that in Europe, not only in Europe, actually, we don't have certification authority bodies that have, and we don't know whether the existing ones for cybersecurity certification will be used for AI certification. For example, ANSI or other certification bodies. So this is something to be seen. The Cybersecurity Act is under review, and we will see how the Commission will deal with the Cybersecurity Act, and if they will embed these AI concerns, the AI certification concerns I just mentioned. So the way forward is to work on schemes for cybersecurity, for trustworthiness certification, to deal with this dynamic nature of risk, of trustworthiness risk management, and how we will collaborate with not only technical expertise, but we need social science, we need the psychologists to deal with the threats that are not technical in the AI system, and the dimensions of trustworthiness that are not really technical. So there is a lot of work to be done, and let me take the opportunity to advertise this Cyber Hot Week we have in Kanyakri between 26th and 30th. Many projects will further tell us their achievements, and also there are hands-on trainings on various cybersecurity topics that apply, of course, for AI systems as well. So you're all welcome to join us there. And with this announcement, I would like to thank you and conclude this presentation.
Thank you very much, Nineta. I will now open the floor for questions, if any. So please, for anyone on the call that would like to ask some questions, I would allow now to please do ask. If no questions, I have one for you. So currently I'm interested, as also we are working in a domain of AI and cybersecurity, but this is very interesting aspect of the certification that you are working in. And my main question would be how you see this certification, AI certification adoption. Do you see some specific use case that the adoption can come first, like front-running use cases that are of more interest, or for some reason can be the ones that the adoption will happen at first place?
Well, Enis actually has published a very nice report on with different cases that we consider and which are more because of course we cannot all at once for all cases. We cannot have schemes. We cannot have appropriate outcomes. So we see ENISA has some use cases built in on AI that we can start with, the most critical ones, because even the AI Act talks only about critical systems. And also lately, I saw a very nice also a set of playbook with a set of use cases we can use. So I think that these projects on AI that give us use cases are very important, very interesting as well to consider and start experimenting with how we can assess all dimensions and how we can actually find matrices and measurements, because it's another big problem, how we can find measurements we can agree upon, because some measurements cannot be technical. CVSS, as I said, cannot measure, for example, social threats, bias. What does high level of bias means? It means something different from you or me or the Europeans or non-Europeans. So where do we agree? Where is the trustworthiness risk appetite? Who sets that? So there are many issues to be considered, because we all agree on the non-technical measurements for the non-technical dimensions of AI. But many, as I said, ENISA, OECD, OASP, many organizations work on these challenges and issues, and we live interesting times. So we'll see in the next years the outcomes.
Okay, thank you very much. This is right on the point. I think the bridging between these social aspects with the technological is very complex. So, as you mentioned, I think that the future will show us a lot of interesting application and how this will evolve in the landscape of the certification for the AI. Our next presenter is David Eklund. So David is a researcher in applied artificial intelligence. He holds a PhD in mathematics and master degree in engineering physics. David, I would leave the floor now to you to share the screen.
Thank you very much. Let's see. That should be it, right?
It's perfect.
Okay, very good. Yes, so I will talk a bit about efficient privacy-preserving feature selection. So this is joint work with Alfonso Iacovazzi, Wang, Apostolos, Pyrgelis, and Shahid Berasa. So the setting here is, so I'm going to start, if we sort of forget about feature selection for a while, and we think about a more general problem, which I call privacy-preserving statistics. So we want to compute a statistic, which I call S, on distributed data. So it's horizontally distributed on K data holders. So I have a little slide later on what horizontally is. But we're interested in what I call the global distribution, which corresponds to the centralized case. That means, let's say we imagine that we have all the data in a big bucket, and that's our data set and the global distribution that it comes from. Instead, now it's distributed over K different clients or data holders. But we're interested in this global distribution. And we want to compute some statistics about it. But the catch is we want to keep the input data private and compute only the statistic S, which becomes public afterwards. And to do this, you can use various privacy-preserving schemes and techniques. For example, secure multi-party computation, that's what we apply in this work. So MPC allows arithmetic over finite fields, if you want, keeping the input data private. So each of these data holders can secret share their data or some derivatives of it that they have computed, and we can compute, say, the statistic or whatever we want based on that without revealing the inputs. Now, a problem here is that even if S is a rather simple thing, so when I say statistic, I mean things like it could be a mean value or a variance or some more complicated statistic about the data distribution. But even for simple things, these procedures are quite costly if you want to preserve privacy, both in terms of computation and communication. So you have to communicate between the different clients. For example, if you do MPC with so-called secret sharing scheme by Araki et al., which is one of the common ones, it requires 1 bit of communication or 1 field element if you want per multiplication that you're doing. Additions are free in this scheme, but multiplication is going to cost you. And the idea here that we're looking at is, maybe instead of computing this S statistic there, we can compute a good approximation or good enough approximation or a bound or something about the statistic, which is good enough for our applications, but is hopefully much cheaper to compute and adapted to this distributed setting. This, I think, will be, if you use these things in practice, it makes sense to think about alternatives like this, where you have approximations or bounds or whatever it is that you need. So horizontally distributed data, well, it means the centralized case is where you have, let's say I have some data set here with 5 features and 1,000 data points, so data rows. And distributed horizontally means that here I have 3 data holders and they get a chunk each here. All of them have all 5 features, so their data points look the same, but the first data holder gets the first 100 data points or rows. The second one gets the next 200 from 100 to 99. And the last one gets the remaining 700 rows. So you have the data points are distributed this way over various data holders. But each data holder's distribution contains the same features as the other ones. Now, an application here that we're looking at of this privacy-preserving statistics is privacy-preserving feature selection. Feature selection is a pre-processing step that you can use in machine learning or AI modeling, where you basically select appropriate features for your task. So, for example, if you're doing supervised learning and trying to predict something based on the features, you want to pick the features that seem most important or useful for predicting the target. And note, it's not feature engineering in the sense that you cook up your own features. You just select, and they're already done, and you pick the ones that seem important. Now, doing feature selection, that can improve the accuracy of the model. It can improve convergence speed of the training phase. It can reduce overfitting and reduce model complexity in the sense that you project to a smaller feature space. You can use a smaller model perhaps to train your to perform your task. So those are the benefits with feature selection. And the simplest technique out there is the filter method. And what you do there is basically you compute a statistic S for each feature. And this is now the S that I was thinking about at the beginning. And this statistic tells you something about how, for example, how good that feature is to predict the target. And you filter out the features where the statistic is less than some threshold value that you have chosen. So you throw away things that seem non-important. So an example of S could be correlation coefficients between a feature and the target, for example. So this would measure the linear correlation, which could be an indication that it's useful for prediction. Other examples are, well, just the variance actually is used sometimes on the feature. If it doesn't vary very much, maybe we can throw it away. And I will mention another one later here, mutual information. So if we return to this setting where we have data horizontally distributed on K clients, now privacy preserving feature selection means that data is distributed like that, and you want to select the features based on this distributed data, but keep the data private, but you reveal only the index of the selected features, or for example, the feature score and the value of this S. So I mentioned variance and correlation coefficients. So another kind of popular feature statistic is mutual information. And that one is a little bit more sophisticated. It's, let's say you have two discrete random variables, X and Y. Then I want to introduce the entropy of a random variable, one of them, say X. And this is a measure, you can say, of the uncertainty contained in X, or the spread of the distribution. So the definition here is the expected value of the negative logarithm of the probabilities. Big N here is the number of outcomes that random variable X can have. And if you have the extreme case where it's very narrow distribution, maybe pi is 1 for one of them and 0 for the others, then this is just 0. And if you have another extreme, like the uniform distribution, it's going to be the biggest for that number of outcomes, which is the log n, log big N. So it measures kind of the uncertainty contained or related to the random variable X. And mutual information is a measure that compares two random variables X and Y. And what it is by definition is the sum of the entropies of X and Y. And here I think of X as the feature that we want to test, and Y could be the target variable in a machine learning model, what we want to predict. You take the sum of the entropies of X and Y and subtract the joint entropy, so the entropy of the joint variable X and Y. So this has to do with how they are related, right? And one way of seeing mutual information is that it measures, in a sense, the information that you obtain about Y by observing X. So that's exactly what we're talking about here. We want to predict Y based on X, and we ask how good is it? How good is X to predict Y? And mutual information is positive or 0. And it's going to be 0 exactly or precisely when X and Y are independent. So that is when there is no relationship at all. So that means X is useless as a feature to predict Y. So the bigger this is, the better in a sense. And 0 means that they are independent. And mutual information is often used for feature selection. Then, as I said, X is a feature and Y is the target variable. And we can, if the mutual information of X and Y is small, we can perhaps throw it away. So let's see. I'm going to check the time here. Yeah. So that's mutual information. I can mention that you can, for example, have that the correlation coefficient between two random variables is 0, but they're still not independent. And then the mutual information will be positive. So sort of the correlation statistic would miss such connections, whereas the mutual information would catch it. So that's when they're uncorrelated but still dependent. So what do we do here in this work? Well, the first observation here is that if we have the K data holders or clients, each one of them has a weight, which you call lambda I here, the K of those, and that's proportional to the number of data points that they have. So that tells you how large portion of the global distribution that local distribution is responsible for. Then it turns out that entropy is concave. So that means that the entropy of the global distribution of X and Y, those are the things we're interested in, is bigger than or equal to this weighted mean value of the local entropies. So this is a general fact about entropy. And the idea here is that, well, okay, so maybe we can pre-compute some things locally in the clients, because that's free in this context. We don't have to use MPC protocols or expensive communications and so on. We can just pre-compute, for example, the local entropies of the various distributions. So the data holders themselves compute this. And a choice here that we make is that we let the total number of data points be revealed so that the clients know their own weights, lambda I, so they can compute this, which is the weighted local entropy. And then the idea is that, well, instead of computing the mutual information using an MPC protocol, which gets complicated or complex, we can compute this bound here, which is the sum of the entropies of X and Y. That's similar to the definition of mutual information, minus L, which is now the weighted average of the local entropies of the joint distributions. So since we have this bound here, we're going to get that B is an upper bound of the mutual information. So we don't compute the mutual information, we compute the upper bound, and then we filter out the values which are such that the upper bound is less than the threshold. Meaning, if that's true, then the mutual information is also less than the threshold, and we can throw it away. However, if the bound is not very tight, then we can get some extra features in there. I will say that again soon here in the last point. There is one thing that's inside of here. The H of Y is actually irrelevant in the sense that it's the same for all features, so you can just throw it away. H of X, the entropy of X, it contains the logarithms, as we saw in the definition here. So to do that in MPC, you're going to need some kind of approximation of the logarithm. And if you want to get rid of that, you can use optionally here, which we do in the paper, use a kind of cross-entropy bound on the entropy. That's an upper bound, to compute an upper bound on the entropy and the whole thing. So you actually replace this by another upper bound. That makes the computation more efficient, but the bound less tight. So it's a compromise there. So caveat here, or a remark, you can say, these approximations and bounds are good when the local distributions are similar enough to each other. So if you have large divergence or a very non-IID distributed data, that means that the local distributions are quite different from each other. The gaps of the bounds or the tightness gets looser and looser. That's in the nature of this, as you might guess, since they're computing the local joint entropies here. So this, what I find interesting here, that the method is still correct if you have what I call divergent local distributions, if they're quite different, in the sense that we will keep the important features. We throw away things that are unnecessary, but we might get some extra unnecessary features which are included if we have non-tight bounds. So that's by the nature of the the idea here of using a bound. So it's conservative in that sense. We throw away unnecessary things, but we might include some extra stuff, which is correct, but it makes the benefits of feature selection less. Okay, let me speed up a little bit here. So a little bit about the complexity. If we compare base, here is just a straightforward implementation of the definition of mutual information in an MPC protocol. For the logarithms, we use you have to do something like a Taylor expansion, like a polynomial to approximate the logarithm, and we use here a Haddei rational function approximation, so quotient of polynomials. If we have a feature with m different outcomes, big N, and a target y with big M different outcomes, and let's say the computation z maps to z log z, which appears in the entropy definition, requires little m multiplications, then the complexity in terms of number additions and multiplications of the straightforward implementation base of mutual information and our methods are like this. So the important row is the multiplications, and this is the version where we use the cross entropy bound. It's actually just big N multiplications compared to n times m times little m with the z log z function in the base case. So that speeds up things quite a lot. And then we did some numerical experiments, and we used this MP-SPDZ framework for multi-party computation, and we used this so-called 2 out of 3 secret replication scheme by Araki with honest majority and passive as well as active adversaries, but this table is for passive adversaries. I have 2 examples here. It's Gizet is a kind of mini version of MNIST handwritten digit identification. It's the 4 and 9 digits, which are similar and a little bit hard to distinguish from each other. SPO2 is a oxygen desaturation data set for oxygen desaturation events in the bloodstream. So you see the no feature selection, the straightforward implementation of mutual information, and our method classification accuracies are similar and they're good. And then for the time in milliseconds here, it's say in the case of SPO2 about 1 second per feature and 7 milliseconds for the other method. And for Gizet, it's about 2 seconds and compared to 30 milliseconds. So yes, I should stop there. Thank you very much.
Thank you. Now would be a good time to ask questions. Anyone from the attendance list that would like to ask something to David? Okay, so since your method focuses on the specific type of statistics, but let's say that if for the real world data analysis, it often needs more flexibility. Do you think that your approach can be extended to other type of statistics?
Yes, I think so. I don't know any way of thinking about it except doing them one by one. I mean, here we use some trick that's very related to mutual information, and there's similar other work where they look at other things, but then it's another observation that you make. So, but I have been thinking about, for example, if you have a mixture distribution, let's say you model your local distributions as mixtures, for example, mixtures of Gaussians, then the global distribution is also a mixture of Gaussians. And you can take, let's say, the clients fit a local model to their own data and secret share just the parameters of these local models. For example, if it's a Gaussian mixture, it will be the mean values and the variances of the components. And then in this case, there are ways to relate the statistic of the global distribution to the components. So in simple ways, for example, in the case of mutual information, you can basically compute I think at least an upper bound of the mutual information of the global mixture distribution in terms of the component data with a simple polynomial. So that may be a little bit more general in the sense that if there is a simple way of doing that, then you can compute your global statistic in a much cheaper way with MPC. Then you only use that to evaluate a simple formula rather than complicated computation of the statistic from scratch.
Okay, thank you. Let's, if we want also for the general audience to try and clarify them and bring closer to them the work you've done. If you need to explain it in short for someone that is not in the mathematical field, for the application of the algorithm, how you wrap it up in the easiest way to explain them how this can be basically applied in some specific settings. And is this your development open source? So I think maybe people that are also in the domain that you're also working can reuse the result of the research. So if it's available somewhere, it also can become of big value to them also to have the access to that.
Yeah, it will be available, I think, very shortly. Perhaps we can put the link in the chat. I don't have it right now, but we can do that. It's part of the HARPOCRATES project. And there is some other code that will be made available there, if I understood it correctly. As far as explain it quickly on a high level, I would say that, I mean, the main issue is you want to do the secret computations where you don't reveal the input, but these are very expensive. And so what we're proposing is try to compute something else. Compute an approximation or a bound or something that can help you solve your problem, but is much cheaper to compute. So consider this alternative. That's what I would say.
Okay, perfect. Thank you very much, David.
Thank you.
There is one question in a chat. I can read it out, maybe. So it comes from Tanasia Gemai. Sorry if I pronounce it wrong. The question is, what's the advantage of the method for privacy compared to a federated learning approach where data are kept local?
Yeah, very good. So federated learning, I mean, then it's a little bit similar to what I just mentioned, where you share just the model. But in that case, if you want to protect against, say, curious central server that has access to all the local model parameters, of course, you don't really know which information is contained there. Maybe it's somewhat obscure and difficult to extract information about the data from those, but you can do it. It's practically doable in some cases. So this is, I mean, secure, provably, except that you reveal, of course, the result of the MPC computation. Whereas in federated learning, I would say, unless you encrypt the parameters, which is another way you can do it, you don't really know which information you're sharing when you share the parameters. You can formulate an optimization problem to try to dig out information about the data that way. And so that's one difference, at least.
Okay, thank you very much.
Okay.
There's also some requirements to share the presentations afterwards, so we can make that available.
Yeah, very good.
So I think we still have for one more, if if anyone is willing to ask. If not, we can go for the next one. Okay, I think we can go for the following one. The next presentation comes from Shen Wang, and the presentation will be about advancing robust and privacy enhanced federated learning in 6G networks. Dr. Shen Wang is a senior member of IEEE. He's also assistant professor and academic director of NETS Lab Research Group, which is a part of School of Computer Science under University College Dublin from Ireland. So Shen, I will give the floor now to you.
Thank you for introducing me, and also thanks for inviting me to give this talk. So firstly, I would like to check if everyone can see my screen clearly.
Yep, it's working.
No problem, right? Okay, good. So good afternoon, everyone. So I'm Dr. Shen Wang from University College Dublin. Together with Madhusanka, we are managing EU 6G SNS funded project called Confidential 6G. So my colleague Madhusanka will be briefly introducing UCD's view on this project later. But for my talk now, I will be focusing on federated learning only. So I will briefly introduce the federated learning concept, and then I will be overviewing 4 of our recent important work that is around the concept of federated learning, and also the challenges that we've seen in the next generation network. Okay, so firstly, what is federated learning? I know most of you already know the basic concept, just but in case that still quite a number of us audience don't know the motivation for that. So in comparison to the centralized learning, where we have super powerful training infrastructure, where you have lots of state-of-the-art GPU card that can train a large model, right? And then you request that the data collector sends the data to you, and then you train the data by yourself, and then you share the data, you share the training model for everyone to use. So while so far it works good, but not always, especially if these data collectors are also data owners, where they have a particular requirement of owning the data and do not sharing the data, especially after GDPR. Whether you are a mobile end user or a financial sector like a bank or a hospital, you have data, but you cannot share the data, right? So in this case, we have seen recently the rising interest of federated learning, where we still keep the data locally for each one of the client machine. As the data collected, we keep it on site. Okay, so instead of sending the data directly to the server for training, we only make the server for aggregating the model updates, while each one of the data collector or the local machine only needs to send the model updates to the centralized server for aggregation. So this distributed machine learning paradigm seems very interesting, working very well, and especially it provides the privacy, data privacy. Well, fat average is the most commonly used server aggregation algorithm. So basically, it does is the server has the initial model, and then step 2 is sends it to each one of the client machine, worker machine who are engaged in this model training, and then they use each one of the worker machine use its own data to train the classifier, so that you can see that at the very beginning they have shared the same model, and after iterations and by iterations they have their own trained model, and then they send their model to the aggregation server, and then the aggregation server do the aggregation and trying to make the universal update. So the commonly used algorithm is called fat average. Is at this step, final step, they just aggregate all of them and make the average. Okay, so everything is perfect, but sometimes it's not. So federated learning claim to preserve privacy well. However, theoretically, it still have a high risk of privacy leakage. Let's use a simple example to explain why. So we all know that machine learning is done by setting up a kind of cost function, where you're trying to minimize the cost. While minimize the cost, you find what is the best model, right? So W is the best model you're trying to find. Xi is your data. Yi is your training data label, and you're trying to minimize this gap. Okay. So let's take a derivative of it and then use a stochastic descent to find the optimal one iterations by iteration. So if you take the derivative with respect to the model parameter W, you will end up with this. Okay, so remember, this is the gradient, and this is your input data, and this is just a constant. It's not even a vector. So it's basically a kind of linear transformation of your data itself. Although you're transmitting what you are transmitting in federated learning is the model update, not the data at all. But because of these, transformation function, linear or non-linear transformation of your data, it is theoretically very possible to reverse your data. Sorry, I see some message. Okay, so I think this question is not about my talk. I will check it later, maybe.
Sorry, it was me. I answered another question.
Yeah.
Previous
No
speaker.
worries. Okay, so given a gradient, then you can kind of inverse its original data, while the local model updates is another kind of simple transformation of the gradient, where you have this learning rate and the previous model. So for the attacker can monitor the training process continuously, so that it is easy for the attacker to guess the previous model. And also, if they keep monitoring the training process, it is getting very easy for the attacker to inverse to infer your training data. Okay, so which means that one of the key motivation of having federated learning to preserve the user's data privacy is kind of uncertain thing. While if we put federated learning in the context of 6G, the next generation of mobile network, we will be facing more challenges, including data heterogeneity, device heterogeneity, and communication overhead. So communication overhead is actually the long-term bottleneck for improving the performance of the overall federated learning system. So if you put it in particular for 6G, then its impact is not that different compared to the general case, while the two heterogeneity issues are becoming very challenging. So what we mean by data heterogeneity is more about its data distribution. So one of the very popular data sets used in the machine learning research is MNIST. So it's basically the handwritten digit recognition. So in IID datasets, which means all the datasets are evenly distributed, which means you can see all type of 10 digits across different device. While if it is non-IID dataset, it means that it's not evenly distributed, which is more commonly seen in the realistic federated learning scenario. In this case, we can see one of the device contains only two types of digit, 10 and 4, and the second one also only contains 5 and 7, and missing the other 8 possibilities. So that's called data heterogeneity, while device heterogeneity means that each one of the device will have different storage capacity, communication capacity, and computation capacity. So to federated learning system overall, it means that the local training delay will be different across all devices. So the central server will face the choice of synchronization or asynchronization. So asynchronous federated learning will have to wait each one of the device to finish its local training to move on to the next iteration. While the asynchronous federated learning, which is more practical, while the scale of the system grows, means that for each one of the device, while your local training is finished, please just send your update right away to the central server for aggregation. We often see the case like this one means that after a few of iterations for most of the machines, it is still not yet finished its first iteration. In this case, normally we face the decision whether we remove it or we consider it, but with a discounting factor. Okay, so that's kind of the basic knowledge of federated learning. This is a big picture of AI-enabled intelligent 6G networks, where it has the intelligent sensing layer, varying data sensors are collecting data autonomously and passing it through the nearest base station to the edge server, where we call it data analytics layer, and then intelligent control layer trying to have the AI embedded traffic control and manage it in a larger scale, and then serving the top layer applications. So when we're talking about federated learning, we're mainly talking about all three bottom layers, although it is up to the edge server or the base station, but the federated learning takes serious consideration of the data and device heterogeneity. Okay, now we're talking about 4 of our recent research work that we think is very important in this area. So the first one we're going to talk about is called RegDef. It was published 2 years ago on IEEE transaction consumer electronics. It is a recommendation-based defense mechanism for privacy preservation in federated learning system. So basically, this paper is looking at inference attack. So we were talking about the privacy preserving isn't always there, right? Then the first work we're talking about is focusing on this inference attack, trying to inference the member or the raw training data, call it data reconstruction attack. So What's new is that we are looking at this attack through time, through the training time, where it's one of the most commonly seen scenario where we have this constantly monitoring network traffic AI-based application. Well, it's very widely seen from the VR-based IoT data sensors, but in the literature, we have seen not this kind of influencing attack in the context of time series is not very well addressed. So basically, what we do is we in this context we devise a kind of recommender system, and we firstly look at this part. We firstly, launch this inference attack that if there is no privacy preserving mechanism is in place, we can see that the ground truth data can be successfully reconstructed. Well, then we keep adding the perturbation called differential privacy, and we're trying to add the noise to it so that the attacker cannot successfully reconstruct the original training data within the reasonable number of iterations. Well, on the other side, if you keep adding a very strong noise, the whole model will be impacted. So we need to be very careful about choosing the key parameters. So here at the left part, you can see that using our recommender system, we can always achieve a relatively stable model accuracy, recall, and F1 and whatever. Well, without our system, you can see that with the training round proceed, although the privacy is kind of preserved, but the model accuracy is a kind of lost. Okay, so that's the first work I would like to share. And the second work is called SHIELD, Secure Aggregation Against Poisoning in Hierarchical Faculty Learning. So one of the highlights of this paper is that we focus on hierarchical faculty learning in particular. So in 6G networks, most likely your data collectors or the end users will be sending their model updates via edge server rather than directly to the cloud parameter server for aggregation. So we've seen the number of existing data poisoning attacks. They are all studied under this traditional star-shaped architecture rather than hierarchical faculty learning. Well, in hierarchical faculty learning, we can see that this kind of difference will be kind of dispersed while the level goes higher and higher. So which means that traditionally this defense is deployed on the aggregation server, and in a hierarchical faculty learning architecture, it becomes more tricky. And then another thing is that we find what's lack in the literature is there are multiple different ways of distributing these attackers. They might attack the whole subnetwork, or they might be scattered around different subnetwork. In this work, we have tested all possible cases, and this work is published last year in Transactions on Dependable and Secure Computing. So this methodology, SHIELD, is trying to achieve the effective poisoner detection and removal, and also trying to keep the original model performance is untouched, which means even if there is no poisoners, the model performance still remains. And it should be agnostic to different data distribution, poisonous distribution, and different types of data poisoning attacks. And it should be robust to a varying percentage poisonous clients, ranging from 0, which means no presenters to up to 99%. So Sheld works in a way like the first few steps are all the same as the traditional federated learning. But after the client finished this local training, they're trying to send to the nearest edge server for aggregation. So starting from the edge server will start trying to perform the defense, where we're using HTTP scan clustering to remove the outliers, and then from the layer L-1, the nearest edge layer, to the top central server, we all using these HTTP scan clustering, trying to remove the outliers. And finally, we use these averages for the model updates. Okay, so as you can see here, so there is a big table to show the key results. We have model accuracy, we have backdoor accuracy, we have the source class accuracy. So NP means no poisoning, P means poisoning. We can see that when there's no poisoning, Sheld can maintain the model performance very well. When it has poisoning, then when there is very little attack, we can see that the backdoor attack success rate is not high, while it is when the attacker percentage is very high, the backdoor attack is successful, while with our Sheld, it is almost completely removed. And also we have tested our Sheld against different data heterogeneity and also different other strategies. And we showed the effectiveness of our method against the full spectrum of poisoning percentage and data heterogeneity. So I will go quick for the final two works. So the third work is called Shipra. This work was published last year in Symposium on Security and Privacy. So the key idea is use XAI, trying to make the poisonous detection and removal more justifiable. So why we need it justifiable is because if we use the existing work, which is mainly based on the similarity-based or distance-based, we find that many benign cases, the local model updates from different clients are different, while they are all benign. So then they might be misclassified in this case, while the attackers will trying to craft the poisoner's model updates similar to the benign one. So which means that we need to introduce XAI. In our work, we introduce XAI so that it provides, using a very small amount of sample data, it provides the correct understanding of the data. And then for each one of the client model updates, we compare and then trying to remove the poisonous part. So compare with most of the existing work, we can show that our ones, the accuracy is very high, even under the very high percentage of poisonous clients. And also we show that, under this attack, so the benign clients, the task is number 3. So the number 3 shows different colors than all other types of prediction results, is because this is the right one. Well, you can see that when it is being attacked, so number 6 should show high percentage, while the number 3 actually shows the highest. Okay. So the last one I would like to share is a peer-to-peer federated learning. In this work, we have we have published one of our recent prototype implementation for peer-to-peer federated learning, trying to address that's the central server single point of failure problems. And if that can be hacked, then the whole system is done. So yeah, here are some key initial results. So we show that using P2P federated learning is actually converge much faster. Is because there are multiple communications channel happened in the same time, so that to speed up the whole convergence process. And also we show that you don't need to aggregate each one of the nodes, doesn't need to exchange and aggregate a lot of models. Maybe only 2 models is good enough so that it can converge to the high level and also it converge quick. Okay, so that's all I want to share today. If you are interested in more of our recent work in our lab, please do follow UCD Nets Lab on our LinkedIn by scanning this QR code. Thank you, and I'm happy to answer any questions you have.
Many thanks, Shen. So now will be a good time for the questions from the audience. I saw one question in the chat. It was about, I'm not sure is it for the previous presentation or for this one, but it was from Bios Gul. Maybe I would just leave it out for people to speak maybe now.
Yeah, I think I got the answer. Madhusanka gave me the answer. Yeah, so.
Okay. So if no other questions, I would also maybe like to ask one related to the privacy in federated learning for 6G, and as peer-to-peer federated learning removes the central point of access, central server, this changed the dynamics completely. And what would you say are the main trade-offs or limitation for peer-to-peer federated learning compared to the common server-based approach?
Yeah, thanks for the question. I think peer-to-peer federated learning is, to me, I think is still at a very early stage in terms of research. Compared to the traditional one, I think it solves this, or it tries to solve this kind of major downside of the, let's say, centralized federated learning. But it faces many problems, which is more about management, ranging from what kind of peers you want to include, so that you don't want the total scale of the peer-to-peer federated learning network out of control. You want each one of them kind of follow your protocol, and also you don't want them to be very small, so that you are missing these kind of benefits. Before, in particular, before we do this kind of work, we kind of thought maybe the network topology matters a lot. Yes, indeed, but if you can fine-tune some hyperparameters like the number of models to be exchanged, then they can actually achieve a good trade-off between the massive communication overhead and also the performance of your model. Last but not least is these kind of privacy preserving things. So in this prototype, we have a bunch of very good researchers. They already trying to add this differential privacy here, and we find that the accuracy is not impacted a lot, but so far we haven't launched any privacy-related attack to see if the privacy preserving level is kind of strong enough. So, which means that this is one of the possible future work to be done. Where in the traditional fantasy learning, you kind of have some good solutions that already can do this well. For example, our first work, right? So yeah, I hope that's your question.
Thank you. This clarifies a lot.
Thank you.
All right. If no other questions, we can go for the following presentation. The next one is Apostolos Pyrgelis, and he will present privacy preserving hyperparameter tuning for federated learning. And Apostolos is a senior researcher at the Research Institute of Sweden, and also a member of the cybersecurity unit.
Yes, hello. Can you see my screen?
Yes.
Great. All right. Hello, everyone. I'm going to talk to you about some research efforts that we're doing within the HARPOCRATES project, and this is about how to privately tune hyperparameters in federated learning. So let me go in presentation mode. Yeah. Right. So the previous speaker nicely introduced federated learning, since it's an emerging collaborative learning paradigm that enables multiple data owners to train a joint machine learning model that is hopefully better, more robust, and more accurate in some downstream tasks. Federated learning was initially imagined for mobile settings. So, for example, Google used federated learning to train voice assistants, and similar applications are found in autonomous vehicles and healthcare. For the purposes of the talk, I will focus on cross-silo federated learning, which means we have a bunch of data owners, typically a few number of owners, like a couple of hospitals who want to come together, join the databases in order to train a more reliable machine learning model. And in a nutshell, federated learning works as follows. You have an aggregation server or a parameter server who initializes a model, communicates that model to the clients, in this case, the hospitals, so each of them holding their respective databases. Each hospital performs a local update on the model using some learning algorithm like federated averaging or federated or stochastic gradient descent. And then the parameters or the gradients or the models trained at each site are sent back to the aggregation server. The aggregation server aggregates that model with a learning algorithm like FedSGT or FedAverage, and performs a step in the model to the direction so that it minimizes some loss. Now, to do this update, the server requires to use some kind of hyperparameters. For example, the learning rate, the momentum, which are crucial parameters to ensure the convergence and the performance of the global model. At the same time, while initially federated learning was assumed to provide good enough privacy protection because the data of the owners doesn't leave the premises of its data owner, recent works, the last couple of years, have shown that actually this parameter server can formulate some kind of optimization problem and actually revert the gradients or the model updates that it receives from its clients and let's say, reconstruct the data that is held by the parties. This is called the reconstruction attack, but other research has also shown different types of attacks, such as membership inference, attribute inference, and the like. So overall, the privacy in federated learning by vanilla federated learning is not well protected. So to address this limitation, there is a parallel line of research which promotes what is called, let's say, privacy-preserving federated learning, and this works introduce privacy-enhancing technologies in the federated learning training process in order to protect the data privacy of its data owner. So typical examples of such PETs are secure multi-party computation, homomorphic encryption, or differential privacy. Each of them work in a different way. For instance, homomorphic encryption encrypts the data and only the encrypted gradients are uploaded to to the aggregation server. Secure multi-party computation might split the data in some intelligent manner so that the aggregation server can only receive the aggregated model and not see any individual model updates from the clients. And differential privacy will introduce some noise to the gradients to potentially thwart any inference attacks that such an attacker might perform. Now, when it comes to tuning hyperparameters for federated learning and privacy-preserving federated learning in particular, there are some challenges. Traditional hyperparameter tuning methods, for example, grid or random search or Bayesian optimization, are becoming quite heavy and impractical for FL, because FL is by nature a distributed computation setting. It requires a lot of computation on the clients and communication among the clients with the aggregation server in order to perform this kind of and performing this kind of tuning process is quite expensive, and it becomes quite significantly more expensive when you have pets in place in order to protect privacy in federated learning. For instance, if you are using homomorphic encryption or multi-party computation, then you have significant computation and communication overhead, which will exacerbate the overhead of any hyperparameter tuning process. Similarly, if you are using solutions a la differential privacy, so by adding noise to some updates, then it means that if you want to tune your hyperparameters, you will also need to do this in a privacy-preserving way, and it will imply that you are spending a big part of your privacy budget just to tune your hyperparameters before even you start training your model. So so to address these limitations, we need some new methods for hyperparameter tuning, which are related to some new methods which are efficient. So it means that we should be able to do the hyperparameter tuning in a single shot manner, ideally before the training starts. We should retain the accuracy and performance of the final trained model, and we should not compromise privacy as part of the hyperparameter tuning process, because if you share information in order to tune some hyperparameters, then this might result to new forms of privacy leakage, as some recent work has shown that, for example, data outliers are particularly prone to inference attacks when you do some hyperparameter tuning. So in this work, we are trying to address this problem by applying a single shot approach that can be done before the federated learning training starts. So our key idea is that we let the clients who have local access to their data sets to do local hyperparameter tuning and identify good or the best sets of hyperparameters that they can discover on their own data by just doing local hyperparameter tuning. Then each client will somehow will communicate this best hyperparameters to the aggregation server, and the server now is supposed to combine these parameter sets from all the clients and try to come up with an optimal global, let's say, configuration for the global model. So there are two main research questions that we are asking this work. So how would the aggregation server combine the client's hyperparameters in order to yield an effective global configuration? And to address this question, we are performing a measurement study where we try to identify what is the connection between client and server hyperparameters. And the second question that we're asking ourselves is how can we enable this aggregation or combination functionality without leaking information about its client's hyperparameters, which, as we discussed earlier, might result to a new form of privacy leakage. To address the second question, we introduce a framework called PrivTuna, which allows you to do the aggregation or combination functionality of the client's hyperparameters in a privacy-preserving manner using encryption. So let's start with the first part of our work, so the measurement study. So we have our method in order to understand, let's say, the connection between client and server hyperparameters is the following. First, we perform local hyperparameter optimization at each client, and we identify the optimal local hyperparameters. At the same time, as part of our experiment, we also perform global hyperparameter optimization using some federated grid search approach, and this we do it to construct some kind of ground truth to identify what are actually the best server hyperparameters that we could identify in a federated setting. And then in order to see what kind of aggregation or combination strategies the server could do, we try a few different approaches that are common aggregation approaches in federated learning inspired by robust aggregation, etc. So we use methods like estimating the mean of the hyperparameters, the median, the trimmed mean, the mean median of the top best hyperparameters, or we cluster the client hyperparameters in such a way that we identify robust hyperparameters which are intolerant to noise and yield good configurations. And as the final step, we compare the results of each combination strategy with the results from the ground truth in order to see which methods work well and which do not work well. So we have a quite comprehensive experimental setup. So we run experiments on multiple types of data sets, typically computer vision data sets used in computer vision tasks like MNIST, extended MNIST, Cypher10, etc. We use, for each data set, we use appropriate model architecture. So we have CNNs, deep convolutional neural networks with varying number of parameters which are suitable to the data sets that we are investigating. And we simulate different types of data distribution. So we assume the traditional IID setting where we split the data set uniformly and equally across all the clients in the federation. And we also simulate non-IID settings where with some appropriate noise or some appropriate calibration, we make sure that the client's data distributions have different label, feature, or quantity skew. And this could correspond to more realistic federated learning settings where each client brings different types of information in the learning process. So in terms of hyperparameters, we focus on two key hyperparameters for federated averaging: the learning rate, which controls like the step size of learning a model, and the momentum, which ensures that we keep a consistent direction when we are updating the model in order to minimize some loss function. So when we do some experiments on the IID setting, so when the data is nicely and uniformly distributed among the clients, we observed some interesting result that shows that actually very simple aggregation functions, such as averaging the hyperparameters identified by each clients, can yield good global configurations for the hyperparameters. So, for instance, we can see in this plot that the learning rate or the momentum, if we average, can be the global learning rate and momentum can be well configured if we simply average the learning rate and momentum identified by each client at their local datasets. And we can see on the final plot on the right that the accuracy of the final model is very well retained on various datasets. Of course, in the non-IID setting, things become much more complex. Things are not so straightforward. So there we tried with a bunch of the other types of aggregation methods like median, tripped mean, or mean and median of the top 5% of hyperparameters. But overall, we found that actually density-based clustering is a good aggregation strategy to identify optimal global hyperparameters. For this particular plot that we see here, which we simulate a setting with feature skew among the clients, we can see that the learning rate identified by density-based clustering on various datasets is on par with what the ideal, let's say, learning rate would be after performing a federated grid search. And overall, in a bunch of our experiments, in the majority of our experiments, we found density-based clustering to be the most robust method for estimating the hyperparameters. Interestingly, we also found some prior work from machine learning community that proposed a different way of deriving the global hyperparameters based on the client hyperparameters. This is called Flora. It's a single-shot method that trains some regression model that predicts the global hyperparameters. And we found that actually our density-based clustering technique is quite on par with that, let's say, state-of-the-art method, as we can see in this plot. So overall, we have a lot of further insights in the paper that I invite you to see after this presentation if you're interested in learning more about the connection between the client and the server hyperparameters. Then at the second part of this work, we said, okay, now we want to do this hyperparameter combination at the server side, but we don't want the optimal hyperparameters of each client to be revealed at the server, as this might introduce a new attack surface for membership attacks, for example. And for this reason, we present Priftuna, which is a novel framework that does the aggregation process under encryption. Priftuna is based on a hybrid version between secure multi-party computation and homomorphic encryption that's called multi-party homomorphic encryption, or MHC for an abbreviation, and enables this kind of aggregation functions in a federated and encrypted manner. The fact that we are using, so essentially each client computes their hyperparameters locally, encrypts those hyperparameters, sends them to the server, and the server under encryption performs the combination strategy that will yield the optimal global hyperparameter. So at the end of the day, the server will only learn the final hyperparameters and nothing more about the client's individual hyperparameters. The fact that we're using multi-party homomorphic encryption gives us two advantages. So it enables a kind of distributed trust. So because of the way the cryptographic keys are generated, only decryption is only possible whenever all the parties collaborate together. So it means that we have a distributed trust setting so that everybody is accountable for performing decryption. And because we are combining a federated approach with hybrid homomorphic encryption approach, we have a balanced balance between computation and communication overhead based on some, let's say, some plain text or ciphertext versus ciphertext operations, and speed up of some expensive operations like bootstrapping by doing some interactive protocols. So let's see how Priv2 works from a high level. So at the first step, we have the secure key generation process. Each client generates a private public key pair, SKI, PKI, and then they collectively use their public keys to generate a collective public key PK, and any other evaluation keys that might be necessary to implement the combination functionality at the server side. Then at the third step, each client encrypts its local results that it achieved by performing local hyperparameter optimization with a collective public key. So, and sends that ciphertext to the server. The server now, he receives all the ciphertext from the clients and homomorphically executes the combined functionality on the encrypted data and communicates with the clients so that will enable the decryption, the collective decryption. It means that all of them perform a local decryption, and so that the global hyperparameters discovered will be decrypted and sent to the server. Now, we used our framework, Priv2, to implement the two main aggregation strategies that we identified as good ones in our measurement study. So we used to implement the averaging called PF-min, the protocol, and the density-based clustering, which is called the PF-dp-scan. So we evaluated this on the data sets that we used in our study, on some commodity hardware and in a federated learning setting with 20 clients, using the CKKS homomorphic encryption scheme configured to achieve 128-bit security. So we can observe from the runtime that, in just a couple of seconds, we can execute these aggregation functionalities like the averaging or the density-based clustering, and with some, let's say, decent communication overhead of a couple of megabytes. Now, because CKKS is not an exact homomorphic encryption scheme, it's an approximate, we also evaluate the precision of the hyperparameters that we uncover at the server, and we see that the mean squared error between the computed and the real actual best parameters is very small, in the order of 10 to the minus 3 and 10 to the minus 4. Just to put the costs of Priv2 in some perspective, if you were just doing federated grid search, so not a single shot approach as we propose, but a federated grid search, to tune the hyperparameters, you need approximately 2 hours of computation. And if you do a federated privacy-preserving pipeline like Poseidon, which is cited in the bottom of the paper, then this would need approximately 150 hours of computation just to tune the hyperparameters and not to do any actual training of the model. So we see that these seconds are quite beneficial for the federated learning process. So to conclude, in this work, we investigated an open problem of how to tune hyperparameters in the setting of cross-silo federated learning. And we did two contributions. First, we performed a measurement study with the aim to understand what is the relationship between the client and the server hyperparameters. And we benchmarked a couple of single-shot strategies that can be used to do the hyperparameter tuning. Then, at the second part of the work, we introduce Priv2, a multi-party homomorphic encryption framework that allows to do the hyperparameter tuning in a privacy-preserving manner, so without leaking any local hyperparameters of the clients, and still being able to derive global optimal hyperparameters for the federated learning process. So thanks for your attention. If you want more information, the paper is available online. Kudos to my co-authors, Natalia and Sinem, who helped in this work, and the source code of our experiment is also available on GitHub. Thank you.
Thank you, Apostolos. Any questions from the audience? You can also unmute and ask directly. I see some of the questions are in the chat. So, Gusten, maybe if you want to ask, or I can also read out the question. So the question was, in the case of the PRIV-TUNA, what happens when the local dataset does not follow EID datasets and the datasets are not properly distributed between the clients? Was the central server successful to hyper-tuning optimization or not?
So this, as I said, I would say this is more addressed in the first part of the work where we do the measurement study. So in the non-IID case, we simulated various skews among the clients, like feature skew, quantity skew, or label skew, or even we tried to put all the skews together, let's say at the same time. So of course we observed that the global hyperparameters are not as optimal as they would potentially be in this case, but with density-based clustering, which is let's say tolerates noise in the tuning process. So we managed to yield good enough approximations of the global hyperparameters. So it's a matter of the method. And in PRIV-TUNA, by default, we suggest to use density-based clustering as the aggregation method, as you would not know necessarily in a privacy, especially in a privacy-preserving federated learning setting, what does the data distribution among the clients look like. So it's better to go for the case that accounts for non-IID.
Thank you, Apostolos. I think as we are a bit behind, we can go for the next presentation. And if you have more questions, you can maybe directly ask using the chat.
Thank you.
Our next presenter would be, if we follow the next session, and this now closes the first session about privacy and security in federated and distributed AI. The second session is about AI and security for predictive and resilient network. And we have the presentation from Dr. Jorge Bernal. He is going to present AI/ML for incident detection and mitigation in 6G network. Jorge is associate professor. He has a PhD in computer science and as well as MBA from the University of Murcia. He's associate professor in the Department of Information and Communication Engineering of the same university. So Jorge, the floor is yours. We cannot
Hello,
hear.
Nineta. Hello, everyone. Can you hear me properly?
Yes. Now, yes.
Wait, can you see my screen?
Yep.
Okay, so thank you for inviting me for this talk. Today, I'm going to basically present you some of the, let's say, research works that we are conducting here in the University of Murcia in the scope of the RIGOUROUS project. RIGOUROUS is a project and stands for security design and deployment of trustworthy continuum computing 6G services. And in particular, in the project, I'm going to basically focus my presentation on the usage of AI for incident detection. in 6G networks. So far today we have seen several research works in the usage of federated learning for different purposes. We have seen some of the, let's say, issues that the federated learning can bring. As we have seen so far, this approach allows a collaborative learning where local agents can work together to compute a global model through several training rounds, and parties share their models with a global aggregator that compute such a global model. This kind of learning is appropriate for complex and very distributed sparse networks, such as the ones that are mentioned in 6G, that are basically composed of several multi-domain, multi-tenant, multi-operator deployments. But as we have seen in the previous presentation, the federated learning faces several challenges, and not only in the privacy part. There are some other challenges regarding the automation and orchestration of those federated learning agents that can be deployed and should be deployed automatically in the whole continuum of the 6G network. I mean, not only deployed, but also the commissioning, reconfigured, ported, moved, and so on. And this is also a challenging problem that need to be faced. In addition to that, there are some issues regarding problem or challenges regarding how we can handle the network traffic in real time and how we can detect the anomalies and attack in the network. As you know, the beyond 5G network or 6G network will be very demanded in terms of latency, bandwidth, and so on. And the monitoring agents need to be prepared for that such amount of data in real time. This is something that need to be also faced. And the privacy issues we have already seen that I will try to avoid to deep into the technical details about the federated learning and the usage of differential privacy, since it's something that has been already addressed previously. In our case, we also apply, in this case, differential privacy to add some noise during the federated learning approach, so that we ensure that the model updates are, let's say, modified somehow, so that we can give statistical privacy guarantees over the data against an adversary. That we have seen, an attacker may try to infer user private data given the gradients and the model parameters that are exchanged between the agents. So in Rigorous, this is the main high-level architecture in the project. We are facing those challenges in a multi-layered and complex architecture that you can see here. The architecture is composed of several planes, and it covers not only let's say the A-based incident detection, but also the whole loop in a multi-domain beyond 5G deployment. As I said earlier, we are going to focus more on the analytics part, but as you can see, and you will see later, because Antonio Skarmeta is also going to present some other insights about the project. You can see here that in the operational part, we have a security orchestrator, which is the main entity of the architecture that is in charge of enforcing security configurations or security intents, translate those intents to a specific configuration and deploy those policies in the underlying managed network in any network segment of the continuum, from the far edge, RAN, edge, core, cloud, and also, let's say, IoT subnetworks and trusted domains and so on. And the idea here is that we are going to deploy in every network segment, in every single subnetwork, those monitoring agents that will serve us to monitor and gather in real time the network features that will be used for anomalies and for the analytics and detect attacks and also anomalies. And this part of the architecture, as you can see here, we start by gathering those metrics in the data monitoring and then processing a flow processor that aggregates that information from monitoring. And once that we have aggregated features for the analytics, then in here in this box that you can see here, we perform that anomaly detection using federated learning. And then once we have detected any suspicious attack anomaly, then we inform through a cross-domain integration fabric, we inform the corresponding domain and if needed to the other upper domains, the attack that has been reported reaches the decision that in turn decide which is the best mitigation to basically to counter an ongoing attack if needed. And for that, the decision will contact again the security orchestrator that will reconfigure the network in real time in order to mitigate the ongoing attack. And this is basically, a short approach, security orchestration, automation, and response for this attack detection and mitigation. Let's continue because to that detection, anomaly detection based on AI, the approach in this case is firstly deploy the necessary monitoring agents for real-time network traffic processing that need to be implemented for processing beyond 5G network traffic. Then also implement the flow processors that will be able to basically aggregate the metrics and so on, and then identify and implement several or different kind of anomaly detections based on AI. In this case, we have developed deep autoencoders for anomaly detection and also deep neural networks for attack classification. As I said earlier, in order to deal with the privacy issue that federated learning brings, we are using differential privacy for obfuscation the model weights. And all of this has been tested using already existing datasets, and also we have already tested this locally here in the University of Murcia in a real beyond 5G testbed that we have. So this is the part of the architecture that basically focuses on the data monitoring and analytics. As you can see here, what we do is basically monitor in real time the infrastructure, and then process the features that we get, and then these data services basically serves as input for the analytics engine. And we have in the project several kind of data services implemented already. And in this case, the data service that we are using is basically the flow processor that is basically gathers and process the monitoring data and generate the set of features in real time that need to be considered by our AI model. At this in analytics side, we have the anomaly detection engine and the attack classification engine. And this model, as I said earlier, has been trained using the federated learning approach. And as you can see here, in order to do that, what we do is orchestrate the deployment of those federated learning in different network segments and in different domains. This is also challenging because well, we need to cover for that security orchestration of federated learning several aspects. And you can see here the general process where from monitoring we get the traffic, perform the training, then using DP we add the noise using some perturbation functions such as Gaussian functions in DP. Then with the new weights, basically we compute the model and a new model in the aggregator that is then later on, once we have performed several rounds, that new model is basically pushed in the agents back so that they can start used for the inference stage. In order to manage the automation and orchestration of the federated learning approach, we had to define several kind of models for representing the federated learning policies, the intents that are used for configuring the federated learning, and also the common data format exchange that is used in our deployment in the project in order to inform when an attack has been detected. And this, for that part, we have defined a common data format based on sticks. Well, regarding the monitoring module, in here we need to face several challenges. Firstly, in beyond 5G networks, we will have multi-tenants deployments, multi-domain deployments, and even multi-operator deployments. In order to manage that complex network deployment, we will need to, or the network need to be adapted to support several kind of encapsulated network protocols. And for that, we are using a VXLAN to basically to represent every tenant that is becoming part of the network. And also, we need to deal with the beyond 5G protocols and 5G protocol, the DTP protocol, and also for making tunnels and ensure security between in the communications. IPsec tunnels need also to be supported. The problem here is that in the monitoring agent, in order to let's say sniff and gather meaningful metrics from the packets, it will need to basically deep packet inspection the headers. And here you can see some example of a kind of packet that is double encapsulated for let's say support the usage of having different tenants in the deployment, and then the user mobility with GTP, and also the if supported in some cases also IPsec tunnels. So in the end, we have several headers encapsulated, and the monitoring agent need to, in real time, go to particular headers and gather some specific fields from those headers that will serve later on for AI-based analytics. These monitoring modules basically gathers, as I said earlier, IP addresses, TTLs, aspect, tunnels ID, and so on. Then the monitoring module, once it has gathered those relevant packet fields, then push that information in our case in a Kafka broker, so that the following component in the deployment, the flow processor, can aggregate the incoming packet information from the monitoring and generate some flow statistics. In this case, we can basically compute the number of packets per transport protocol, the number of packets per application, the flow duration per protocol, percentage of packets of a given protocol, and so on. The main purpose of this model basically is to feed in real time the detection system I mean, the AI-based autoencoder that we have that has been trained with FL. Okay, and this is basically the general picture of the deployment. Here you can see in each of the clients or federated learning agents that we have each of those compute locally the model, share the weights with a central aggregator that for each iteration it updates the model and send back the model to each of the clients. If you want to have more information about this algorithm, and you can basically go to this publication of ours where we combined data differential privacy and federated learning for anomaly detection. Well, in addition to that, the detection, we need also to orchestrate the federated learning agents. In that case, for that purpose, we have developed several algorithms in the security orchestrator, and that basically will be able to decide where and how is the best way of deploying those federated learning agents. And also, in addition to that, in addition to the orchestration, we need a model to represent the FL deployment, and also that common data format for representing an alert once it has been detected by our system. Here you can see a screenshot of the policy model for federated learning representation that we are following in the project. As you can see here, well, our model allows to indicate several parameters about the kind of learning model, if it's supervised or unsupervised, the number of encoder layers, neurons, and so on. And also the obfuscation mechanism in this case for this example is differential privacy and so on. And this is a kind of policy or intent that can be defined by an administrator, and this information is pushed in the orchestrator that will in turn deploy a federated learning agent in the network using this intent. This intent can be generated not only by the administrator manually, but also can be automatically generated in, let's say, in real time by the mitigation manager, so that we can reconfigure the federated learning agents and deploy a new federated learning agent, and so on. This is basically the mechanism that we have in order to allow interoperability in Rigorous. And regarding the data format for anomaly representation, what it is used once we have detected any anomaly or attack. The model itself is variable, so that in some cases we only report an anomaly, and in some other cases we will need to report a specific kind of attack. As you can see here, we have fields to indicate from the source IP address of the attacker, if known, and so on. Okay. What kind of attacks we are facing? We have tested this approach against several kind of attacks, either in the user plane or the control plane. For the user plane, we have, let's say, run several DDoS attacks, such as SIM flood, UDP flood, ICM flood, and some other slow rates, slow risk attacks. And also we have also tested the deployment and the detection using scanning attacks, using in this case Nmap for running the attacks. In the control plane, we have also tested the anomaly detector for basically detecting some AMF crashings using various techniques and DDoS attacks, such as for instance use re-registration or deny of service via crafted UI attachments. This is basically a representation of deep autoencoder that we are using for the anomaly detection engine. As I said earlier, we have several detection engines onboarded and at the same time trying to infer if there is an attack or not. And this is basically the representation of the deep neural network that we use for the classification. We have, as I said earlier, already evaluated the whole approach. Here you have one of the publications that we have in this field. As you can see here, this is basically the kind of metrics for accuracy, recall, and F1 score that we got when applying federal learning using DP with different kind of configuration of noise. And also for the orchestration, we have tested the approach in order to orchestrate an increasing number of federal learning agents. As you can see here, we deploy and configure the federal learning agents across the different domains, following a linear trend. This is basically what I wanted to summarize here today. If you have any question. Nineta, are you here?
Yes, I'm expecting any question from the audience, and can give them maybe a few seconds to ask. If not questions in the chat, I have one question for you, Jorge. One of the toughest part of incident detection is handling these events that happen very rarely. Did you took this into account? How would your algorithms and system deal with these rare incidents that are hard to learn from?
I mean, we try to, and that's why we have several different kind of models. In some cases, we only detect an anomaly, and we are not able to classify the specific kind of attack. But in our case, in University of Murcia, we are defining different kind of detectors, and also some other partners such as OLU, OneSource in the project. They are also developing their own models, so that kind of approach allows to ensure that in any case we will try to detect the anomaly, because for instance, OLU, they are using some other kind of perturbation mechanisms using multi-party computation and so on, with different configurations, hyperparameter configuration and so on. But in general, we managed to detect so far properly the kind of attack that we have tested. But yet, the challenging part as well is, for instance, trying to implement and adapt the monitoring agents, for instance, using eBPF, P4 languages, and also even directly in hardware, try to monitor in real time highly demands of 6G network traffic, so that we can gather on real time the metrics that will be used for the detection. This is basically also very challenging.
All right. Thank you for your reply and for the great presentation.
You're welcome.
Now we have another great presentation from the project called Fidelity 6G, and it's about using the blockchain for decentralized spectrum access. And the presentation will be done by Madhusanka, who is associate professor and also Adastra fellow and director of NetSlab Research Group of School of Computer Science, University College Dublin, from Ireland. Madhusanka, I will give floor to you now.
Hello. Good afternoon. Can you hear me well?
Yes.
Okay. Yeah. So I think I'm going to talk something different than we have discussed so far, because we were talking a lot about AI. So now I'm going to talk about another technology we are considering under 6G development, that is blockchain, and how blockchain can be used in different 6G application. And this research work is conducted under the confidential 6G project, which was funded under 6G SNS. And in this project, like, we are looking at like how the blockchain can be applied in the different use cases. In this particular work, like, I'm going to discuss how the blockchain can be used in order to enable this decentralized spectrum access, so decentralized dynamic spectrum access mechanism. And the different works we have done under this topic. So the radio spectrum, it's a natural resource, and it is very expensive natural resource, and it has to be managed properly in order to enable this optimum wireless communication. So we are trying a lot of things to improve, like how we can improve the capacity of the communication channel, how we can use gain from that channel, but we haven't actually optimized the usage of this radio spectrum. So you can see, like, in the current scenarios, like the spectrum usage it's about like 6 to 8% occupancy. Most of the time, radio spectrum is underutilized because of these centralized spectrum allocation policies. So that means, like, even though we try our best to improve this the channel capacity, still the radio spectrum is not fully utilized. We have a gap that we need to fill. So as I mentioned, it's a very expensive radio spectrum. So, for example, Germany raised like 7 billion euros just from the 5G spectrum auction. So that's like one of the reasons, like, the people who bought the spectrum, they don't want to share with others. So that's actually create this problem, having this kind of white hole which are not available for others to use. So how we can solve this problem, actually? So there are many solutions already proposed, especially this dynamic spectrum allocation scenarios. The idea here, like, instead of allocating a static spectrum allocation, we go for a dynamic spectrum allocation. We will analyze the usage of the users. According to that, we can allocate the spectrum according to the need. So either this can be done directly with the regulators of these countries, so they can dynamically allocate the resources, or otherwise the primary owners of the particular spectrum can lease the spectrum for the secondary users. It can be permanently, or even it can be like a temporary. It can be leased to the different secondary users. There are many schemes has been proposed for this dynamic spectrum access, like pro-primary spectrum sharing, cognitive radio, spectrum access system. There are many other solutions available to enable this dynamic spectrum allocation. But it is not widely used all over the world, so there are some issues we need to be addressed. So one of the issue we are facing is like untrusted stakeholder ecosystem we have in this dynamic spectrum allocation. So how we can ensure, like, the whoever buy the spectrum adhere the contracts established by these primary users, because without involvement of the regulatory body, you have to sell the spectrum. Then how you can deal with the conflict of the spectrum usage. So these kind of issues has to be resolved. So we need to have like a much flexible and automated way to resolve these kind of conflicts. And also, we don't have the real-time spectrum misuse detection system. Most of the countries, they are using the manual spectrum spectrometers to analyze the spectrum and try to find who is illegally using the spectrum, but it is a time-consuming process and it is not automated, and also most of the spectrum violations are not going noticed due to this system. And the next problem is the bad data issue. That means whatever the spectrum information you are collecting from the different users are untrustworthy or maybe corrupted or maybe manipulated. So that's actually lead to corrupt the whole dynamic allocation, spectrum allocation process. For example, we can use AI-based spectrum allocation mechanisms, so we can automate this process. But if you don't have the enough and trustworthy spectrum information from all around the network, so this kind of system is going to be failed. So we need to address these issues if you want to promote this dynamic spectrum allocation. So there are a few technologies has been discussed in this domain, and especially under the confidential security project, we were studying about this the potential use of blockchain in order to mitigate this issue. So as a first step, like we did a comprehensive analysis, like where the spectrum allocation, the blockchain has been used for the spectrum allocation. So we identified the 4 key categories. One area is the spectrum trading domain. So we know the blockchain has been developed has been used in many areas to create the marketplaces, so where you can sell and buy the different kind of resources. So we can directly adapt this concept on top of the spectrum sharing, so we can create a reliable marketplace. The users can sell and buy the spectrum. And another area is like the secure database and policy enforcement, like how we can automatically deploy the spectrum management policy and how we can analyze this data. So where we can store this information. So the blockchain is a nice tool. We can keep this kind of nice secure database where we can keep this policy enforcement. And also the smart contract feature, which is supported by blockchain, can be used here to automatically enable these policies. And the third area, we have analyzed the spectrum sensing. So that means like how we can collect the spectrum information so we can later use it for example, optimize the spectrum sharing algorithm, or even to detect the misuse of the spectrum, illegal usage of the spectrum. In this kind of setup, actually, we can use the blockchain to collect the information across the whole network because of the distributed nature. And also we can create a new consensus mechanism which can be customized and focus on the spectrum information collection, so that will motivate the people or users to do more and more spectrum information collection. And the trustworthiness of these collected data can be ensured with integrating like machine learning algorithm, certain machine learning algorithm, or there are several methods to do that. And the last part that the blockchain can be done is can be used in the dynamic spectrum management or access control is the spectrum access. So how we can enable the automatic access of the spectrum, and how we can enable the coordination, management, and orchestration of the spectrum management system. That can be also done with the support of the smart contract. So especially when we have like a ecosystem where multiple mobile network operators or the different stakeholders to communicate to enable this spectrum allocation system, the blockchain-based smart contract is a nice tool which can be used in this domain. So after we analyzing these the areas where we can contribute, and we started work on several ideas. So I'm going to show 2 of the ideas which we have discussed. So one of the idea we were trying to eliminate the limitation of adapting blockchain in this dynamic spectrum allocation setting. So we know already from the survey that the blockchain is a viable option, but it is facing several implementation challenges when you are trying to deploy. So one of the things is like the expensive blockchain operation. We know like a lot of discussion is going on, like the consensus algorithm is energy consuming. It required a lot of processing power. So that's one of the big problem. A lot of people is avoiding the blockchain-based system. And the second problem is like already existing blockchain system, they don't collect the spectrum sensing information, which can be used for the misuse detection or the optimization of the dynamic spectrum allocation. So having this thought, like we were thinking of designing a new consensus algorithm for the blockchain, so we can be tailored basically for the spectrum access in order to collect the spectrum information throughout the network. At the same time, it will have a reduced resource utilization in terms of energy and the cost. So we came up with this proof of sense idea. So this idea, we have two versions, centralized version and the fully distributed version. So we were publishing these papers in two transaction papers. So the basic idea of this proof of sense is like, so I will start with the centralized version, so it's much easier to understand. So here what we do is like the regulator is creating a session key, some kind of secret key, and he will be divided that secret key into multiple small parts. And after that, it will be asking to different mobile operator to transmit this key throughout the network. So all the miners, so the miners can be the mobile operators or even third-party users who have the capabilities to listen to the wireless channel, is try to capture this key part, which will be transmitted periodically by the regulator. It will be automated by the blockchain smart contract, the transmission process, and this miners is trying to listen and capture this periodically transmitted key part. At the same time, not only he's collecting the key part, he also collecting, the miners are collecting all the information about spectrum information which is happening in the network around within the range of the spectrum scanner. So after that, whoever the miner who collect the enough number of key part, so we are defining a threshold. So who has the enough number of key part becoming the winning miner, and he can create a new block because he has the complete key. So before he creating the key, he will be including all the spectrum sense information. So actually, the information will be stored in the off-chain storage. After that, only the hash values will be included in the new block. So once the new block has created by the winning miner, it will be broadcast to the other miners so they can verify easily because they also have the key parts receiving from the regulator. And if the block is legitimate, it will be added to the blockchain, and the dash session is over, and we start with the new session. So the main innovation of this work is we came up with this new consensus algorithm. So where the miners are motivated to collect the spectrum sensing information rather than focusing on computational heavy cryptographic calculation. And also we create our own mining devices as spectrum sensors, so we can demonstrate this work, this consensus algorithm is working. So we have created 5 miner nodes, and we try to run this system. And basically we use the HackRF SRDs, which is coupled with Raspberry Pi, so you can perform the blockchain operation. So we have done this kind of demonstration, demo setups, and then we done some experiment to see what is the energy utilization. We have done a lot of experiment. I just want to highlight the energy utilization here. So here you can see the proof of sense has the low energy, quite similar to the proof of stake kind of blockchain system, and it's very much lower than the proof of work like Bitcoin type of network. So this is only for 5 zeros in the hash puzzle. So if you go about the normal operation where we have 20 zeros kind of complex hash function, hash calculation, so this energy will be very, very low, very high. So we already shown like we can motivate the miners to collect the spectrum information using our consensus algorithm, and also we can motivate. We have reduced the energy consumption of the running the consensus mechanism. And another important factor we need to consider if we have like a good consensus algorithm, like how we can fine tune the block generation time, because we don't need the blocks to be generated every second or so something like that. We need to have control over how fast the block can be generated. Actually, we have studied like what are the features we can use in order to control this block generation time, actually we found the three main components: the cryptographic key part, we can change the key size, the length of the key, number of share threshold in order to increase or reduce the block generation time. And the wireless channel quality can be also impacting on like how fast the consensus algorithm will be completed. And also the capability of the transmitter and receiver can also contribute, like how well these how fast the keys can be recovered. So this is actually showing like our consensus algorithm can be modified according to our requirement. So we have, as I mentioned, I have explained only the centralized version. So we have a fully distributed scenario as well, which was published as an extension of this idea. And that's the first work we have done. And the second work we were looking at like how we can address the issue of verifying the ownership of the spectrum when we are trying to sell or buy the spectrum. So when a secondary user will want to buy the spectrum, he need to verify the ownership of that particular spectrum. And also but the problem here in this kind of ownership verification, we need to contact the regulator. That's the only way we can get to know who owns the particular spectrum for a particular region. So that's actually some kind of issue, and also it can be like a privacy violation as well. And this delay will discourage the people to sell and buy the spectrum. And also, it is not a fully automated system, so you need to have like a manual communication with the regulator. So this kind of setup is not suitable when we are going for a fully automated or fast or AI-enabled kind of spectrum management system in 6G network. So we were thinking about a solution for that. So the blockchain actually supporting this non-fungible token concept. So non-fungible token concept can be adapted here in order to support this dynamic spectrum management, mainly to verify the ownership of a certain spectrum chunk. So the idea of a non-fungible token is a token which can be stored inside the blockchain. So basically, each non-fungible token is representing a physical entity, and each physical entity should be unique. That means you will have a unique non-fungible token. So we can actually use this concept to manage the spectrum as well. So each chunk of the spectrum can be a unique resource. We can create a unique non-fungible token for that. So we use this Spectra NFT scenario, so we can leverage NFT concept, and we can have a unique way to show the ownership of a certain spectrum chunk owned by each operator. And it will be easy to verify, and we can be automated with the smart contract. So ownership can be transferred very easily with the non-fungible token. So this concept is very handy. So we went one step further. So if you have a non-fungible token for a certain spectrum which you bought from operator or whatever, so then we propose another type of digital token. We call it the digital permission token. So we can even divide this non-fungible token into a smaller feature. So you can sell a part of the non-fungible token for a certain users. For example, like if you own if you own a token for a certain channel, so you can sell that channel in the daytime for one user, and you want to sell the same channel for nighttime for another user. So in that case, in that kind of scenario, so you can use the digital permission token to create two NFTs, equivalent NFTs to sell these two operators. So that's the idea. So we want to further divide this non-fungible token ecosystem into fine-grained management of the spectrum. So this is the proposed architecture for this non-fungible token creation process. So the first step is like the regulator has to adapt this non-fungible token scenario. So each chunk of the channel will be created with the unique NFT. So the regulator will mine this NFT and store this information, the meta information in their blockchain network. After that, these regulators can do the NFT auctioning. So the primary users can place the bid and he can buy the NFT directly. This process can be also done within the blockchain marketplace. And once the primary users has this the token which is bought from the regulator. So if they, for example, if this primary user wants to sell this token into multiple operators or multiple secondary users, so he can mortgage basically this primary NFT and create the several permission token according to his requirement. We have a smart contract to keep this NFT blocked and create the multiple permission token, and then the primary operator can sell this permission token to the other secondary users. So it can be also done with the token auctioning process, quite similar to the previous NFT auctioning process, but in this case, you don't need to get involved with the regulator. So each primary user can sell the spectrum. So the idea of using this the primary so permission token actually enhance the granularity of this spectrum sharing model. So you can see in the normal scenario, the regulators will sell the bandwidth for a certain region. So basically, the same bandwidth is allocated for the whole region in the country. But with the permission token scenarios, we can go with the three more aspects like bandwidth, region, and time, and all three parameters can be adapted in order to create the permission token. This is just the example. If you want more parameters to be considered, that can be also done here. So the preliminary results already shown like we can have like a better revenue generation because you can optimize the spectrum sharing in the NFTs, and also the utilization of the radio channel frequencies is also increased because now you do very fine gain channel allocation with the permission token. So that's it from my talk. So, and I will take 1 minute to advertise like one of the event which is organized by our team, which is called the SecureNet event, Security and Privacy and Future Mobile Network event. So we are running this for the third time. This is a free event, and which is also organized with the collaboration of the Robust 6G project, another 6G SNS project related to this. So this is the one-day event. So we have its hybrid mode. So you can either attend at UCD in person, or you can join online to listen to our talk. So we have a very nice set of speakers who will be presenting quite similar to this event. So thank you very much. So if you have any questions, so please feel free to ask, and also please follow us in the LinkedIn to get updates about our work.
Thank you, Madhusanka. Now I would kindly ask the audience to ask any questions. You can raise hand or unmute and speak directly. You can also ask on the chat. I will need to double check if something is already available there. So I'll give people some time. If no one will going to ask, I also have some questions as well. So, Madhusanka, my main question about the last part of your presentation, where you explained how you use non-fungible tokens for this dynamic spectrum management. So what would be the main challenges of implementing this in real world deployments? Is it about from the telco side, the adoption, or there are some other maybe technical challenges that are not directly seen through what you explained?
Yeah, I think the main challenge of using this blockchain-based NFT in the real world is the regulation. So I mean, for the moment, like the dynamic spectrum management is not regulated in most of the countries. I would say like almost all the countries are not using this dynamic spectrum management. So So the adaptation of blockchain comes after that. So I think the main limitation we see here is the regulation barriers. So there was like some discussion in several countries. For example, like FCC in US has discussed the adaptation of blockchain to enable this dynamic spectrum management, but it haven't happened yet. So I think the main limitation is the regulation. Otherwise, the technology is already there. So just we need support from the regulators.
Okay, thank you for clarifying, Madhusanka. If no other questions, we can go for the next presenter.
Okay, thank you.
Thank you very much. So our next presentation is related to threat and security enablers for predictive 6G network, and Fotis Foukalas will going to present. Fotis is a technology advisor for 6G and AI at Cognnin Technologies.
Yeah, I'm here. Can you hear me?
Yes.
Okay, so I can share also my screen, I guess. Okay, can you see my screen?
Yes. Just put it please in the presenter mode. It's perfect now.
Okay. Okay, just a second. Now it's better. Okay, okay, I'm going to present you some results that we have from the Predict 6G project that is about predictive 6G networks. I'm from Cognnin, an SME in Greece that is working in 6G and AI together or separately. And I'm going to talk with some aspects and enablers regarding this type of networks. So in order to introduce you with the Predict 6G, I would like to share with you this architecture where the main elements is the AI control plane that you see there up on the right, AICP, and we have also the management domain plane is the down right side, MTP, where at the end we have an end-to-end management domain architecture. I would like to stress that Predict 6G is a management architecture for 6G network, so it's not the actual 6G network. And you see here how through AI and the control plane we can manage several services starting from registry, discovery, time synchronization, monitoring, and so on and so forth. I would not like to go into detail, but the fact is that we have the end-to-end management domain. And then at the bottom, we have the different management domains, where I would like also to mention that the management domain, imagine that is a different technology. For example, we can aggregate 3GPX technology, YZ, we can aggregate Wi-Fi, we can aggregate time-sensitive networking, and so on and so forth. And this is a multi-domain network eventually. Of course, we focused and as a company to the security aspects, and the architecture itself raised many problems, and we have to deal with different threats that I'm going to list you after this slide. But in general, there is in two different parts of the network of the architecture issues. For the AICP security aspects in the control plane that is driven by AI, and that's why we mention here that we have also security issues on the AI itself, and in general on the overall procedures of managing the different services for all of these domains. And of course, as I said, there are issues also for the management domain plane. Here we have a list of different threats that we analyzed at the beginning of the project. For example, detected incident reports that should be shared across the domains, application data flowing through the network, and different flows over there. Programmability of the network services raise also issues, security issues, and here we have different causes and mitigations of them. Next, we have also issues on the authentication because its domain should be also authenticated and should talk to each other. We have service-based security problems that should be addressed at the service level. And finally, but not the least or the last one, we have identity-based cryptography and issues related to this. Since we have cross-domain authentication and many other functionalities that in a normal network, it's not multi-domain, but it's in single domain, and all of these things should be managed. Finally, we focused on 4 different mechanisms, I would say, or security enablers that are really very common and important, like authentication, integrity protection, message protection, and path redundancy. And I'm going to show you some technical details about these 4 mechanisms. And finally, I'm going to finalize with the AI security part. Okay, for the authentication, we have a management service that is called end-to-end authentication management service. I guess you remember the figure, the first figure, so the architecture is following this artifact, let's say. So at the end-to-end management domain, we have the service, and at the actual management domain plane, we have the registration authority, the certificate authority, and the distributed ledger. Why? Because we suppose that is, and we propose actually to have blockchain in order to make the authentication. So from this point of view, here you see a flow chart of the first part of the certificate, that is to issue the certificate. So there is through the end-to-end distributed ledger that resides on the end-to-end management domain, and the fact that you have the registry authority, certificate authority, where one, here we consider the management domain 1, and I'm going to show you afterwards how you can really authenticate, given that you have the certificate, you authenticate to management domains that you will see 1 and 2 as a number. I'm not going into detail. This procedure to issue the certificate, it follows a blockchain type of procedure. Then we have how the authentication is carried out. Here you see, for example, the management domain 1 would like really to be authenticated by the management domain 2 and vice versa. And this will take place through the end-to-end management domain again entity. Where you see again the registration authority and the certification authority of management domain 2, where the management domain 1 is asking for the different private keys, and finally through the certification that has already has and signed is getting the public key, that is the PK1, and is asking the certification ID from the management domain to certification authority. This continues and going from the management domain to certificate authority to end-to-end distributed ledger that query the certificate info that are coming back to the management domain 2, and that compares all of this has and signed certification 2 with the public key of 1. And finally, the management domain 1 has the certification of the management domain 2, and that's we have the authentication between 2 domains, and this could be really generalized in multi-domains. The second mechanism that I mentioned before is the shared key, where we assume a pre-shared key exchange technique that it's pretty much known for integrity protection. And here we see, for example, through again the end-to-end distributed ledger, the management domain 1 and management domain 2, and how they really shared their keys. This is actually integrated in the former procedure of the authentication, so it's not separate. Actually, it's at the beginning of the authentication. But anyways, normally you study this separately. And here, if you go through, it's the normal procedure of shared key. And I would like really to start to stress that we assume that it's better to have PSK rather than PKI, that is the pre-key infrastructure technique. But here we prefer the PSK because PSK is simpler and faster for environments where all participants are known ahead of time and reduce overhead from certificate issuance and revocation. So when to use PSK in blockchain rather than PKI is private or consortium blockchains, known and limited number of nodes. That is our case because, we're not going to have many domains. Control environments, that is again control because they're under the control of the operators, and real-time systems where latency is critical and predictive means low latency. And by the way, the time-sensitive and deterministic networking is part of the predictive 6G networks. The other mechanism is the message authentication code for integrity protection is the known MAC sec, where here again we show how this can be done between the different management domains. Here is known that you include MAC algorithm inputs in the normal packet format, like with header and data, and all of this taking place in the different domains that using the MAC algorithm check whether there is the shared key, and that's why it's verified per domain. Otherwise, it's cancelled, as you can see here, as long as this does not hold. Now, I'm talked about authentication, shared key, and also message protection. Now I'm going to another that is all part of the authentication process. Now I'm going to another topic that is the path redundancy that is necessary in this kind of multi-domain networks because the traffic should really find another way through the multi-domain network. So the path redundancy is important for geographical distributed networks, for load balancing requirements, for failover mechanism, resource optimization, and a multi-layer AMF redundancy strategy is followed in our case. If you notice that, I guess you have not done, in the first figure, there was also a path computation service in the end-to-end management domain. And I show you here how all of this process of path redundancy is leveraged by the predict6G architecture through the path computation. And consider that this is deployed in the management domain 1 and is also collaborating with the discovery service. And I'm going to show you an exact example of how the path redundancy could be really provided by the predict6G architecture. For example, is getting the end-to-end topology, as you see number 1 in the flow chart, that ask the MD path computation module that I mentioned before. This is going through the end-to-end service automation, through the end-to-end path request, and so many messages here between also again the end-to-end path computation, because by the way, each service has also end-to-end path computation, end-to-end service and management domain service. That's why you see end-to-end and MD, in order to not confuse it. And the end-to-end path computation is all of this process that is actually a particular algorithm that was devised by a partner for the project. And finally, the path redundancy is really provided through another path selection that is coming at the end of this process. Okay, finally, I would like to talk about the AI and in the AI features of the PredictSIG, because you noticed that it's an AI control plane that we proposed in the project. First of all, and most importantly, we have predictive type of AI attacks. And this is what we studied mostly. And we have identified some of them here in the table that I have included in this presentation. So you can have training data control, you can have attacks to training data, to source code, to test data, to model control, to label limit and query access. And the integrity is violated with a certain poisoning procedures, let's say. And the objectives is definitely to provide support on this poisoning and attacks on those AI type of functionalities. Okay, this is my presentation about what we have done in terms of security mechanisms and enablers in PredictSIG project.
Many thanks. I will now again open the floor for the questions. I don't see any hand rise, so I can maybe also ask another question related to the presentation. So you're introducing security enablers for these future networks, and I'm wondering, how do you evaluate whether this security technology actually work in dynamic and real-world environment and real-world network conditions?
Okay, first of all, I have not shown you here results of our studies for sure. On the other hand, we have not really validated all of the mechanisms because it was not also in the plan of the project. So we have really, as I told you, evaluated the path redundancy mechanisms, the time synchronization that I have not shown you here. And finally, there is a validation methodology, security validation methodology that one partner of the project, the Polytechnic of Torino, is doing, and has done a thorough study of authentication mechanism and whether it's really secure, it's not really vulnerable to the threats and the attacks that could happen. But I couldn't really include all of these things in here, and that's why I focus mostly to present you specification related contribution rather than actual algorithms results.
Okay, this is fully understandable, and thank you for your reply.
Thanks a lot.
Okay, with this one, we close the second session, and now the goal is to go to the session number 3, which is the last session about security and privacy management in next generation network orchestration. The first presentation comes from Rigorous projects, and it's about DevOps security development, deployment and security and privacy in multi-segment networks. The presentation will be given by Antonio Skarmeta. Dr. Skarmeta is a full professor at University of Murcia, and he leads the department, the security. So I will give the floor now to Professor Skarmeta to present their work.
Okay, many thanks. Let me put the presentation mode. Okay. Yep. I hope you can see it.
Yes.
Perfect. Okay, So many thanks also for the invitation, as my previous colleague, and also for the nice webinar that we are having. I think that there's a lot of different issues that have been raised and are interesting to discuss also. So in my case, I'm going to present you basically the another approach or another aspect of the Rigorous project. As my colleague already has mentioned, basically our project is Rigorous is the name comes from the secure design and deployment of trustworthy continuous computer 6G services. And basically what we want to focalize here in this presentation is more on the aspect of how we are envisioning to go from the specification of the requirements that the different application and third-party applications need from the security and the privacy part, and how they can be taken into account on the orchestration of services, but also in the enforcement of the different aspects of the infrastructure in order to monitor, check, and verify that all these security and privacy requirements are being compliant and they are being correctly taken into account in that sense. Okay, so basically, in order to do that, and in this case, I think it's important to understand that in the case of Rigorous, we focus from the beginning with the idea of this, how to provide a full DevSecOps operational environment that can be fully integrated on the management of the future networks in that sense, taking into account as, for example, not only the aspect purely about security and privacy, but also taking into account, for example, the use of AML and AI algorithms that can help on the process of managing all these different aspects of the DevSecOps operation in that sense. So at the end, as you will see later, we have defined an architecture that a little bit try to cope with the different components and how they work together, so that we can go, as I said, from the specification that you can see here on the green part of the design of the picture, where the user, and what I mean the user, it could be a third party, it could be a service, a network operator that wants to use certain service on the infrastructure, is able to specify basically certain security and privacy requirements, and then from there, how to do the onboarding of this requirement in this case on the operation in a multi-stakeholder, multi-domain scenario. So as you can see here, the idea also is that we are orchestrating not only basically just one domain, but also several domains that could take into account different aspects or different part of the network in that sense. Saying that, basically, as I said, this picture at the end here, I can show you the high level, I would say, the vision of the architecture, where we identify through the evolution of the project different subcomponents and different building blocks that are necessary in order to be able to cope with this objective that you can see here linked to the architecture. So how to provide a framework that supports the security on the continuum. So at the end, the important thing is also, as I already mentioned, not to just cope with one only domain, but also to be able to deploy and enforce privacy and security requirement for the service over different domains. So to take into account the difference and the differentiation that we can have on the different domain regarding the components and the solution that already are being provided. How to facilitate this human-centric IPsec vision. So the main idea, as I mentioned, is, and this is why we have this green layer here, is to provide a combination of enablers and supporting tools that facilitate all the process of the onboarding, the specification, the definition of the intents, and at the end also to provide the feedback to the end user, so that we can also provide information about certain threats that already have been detected, and maybe to support the identification of new mitigation actions that need to be applied in that context, in that sense. And finally, as I said, some of these components are already presented by Jorge previously. At the end, the objective of this deployment phase that I already mentioned and the enforcement could imply that also as part of this specification and requirements that are being provided by the network service, is that you need to deploy in certain part of the network some enablers that should be in charge of analyzing basically the behavior of the network as such, or the subnetwork, or either of certain components of the infrastructure. So to try to detect certain kind of anomaly behavior, and based on this, launch the possibility of identification certain strategies and that can be taken in order to do a mitigation, and based on this, come back again to a new enforcement, maybe of new component that should try to react to that mitigation or provide solution for the mitigation and react to the possible abnormal behavior that is happening in the network. Additionally, and part of this this schema is also to take into account that as we are able to analyze and evaluate the impact of this mitigation strategy that are being applied as a consequence of the specification being provided by the user. Also, we need to be able, and this is what you can see here about this digital twin, we should be able also to understand if a different mitigation strategy should have been applied, and based on this, be prepared for the future to new possible strategies or plan new strategies so that they can be taken into account when a similar situation is being identified in that sense. So at the end, you can see that we have a combination of components basically that are in some sense managing not only the orchestration, managing the enforcement, doing the analysis of what is happening, and based on this, being able to provide certain reaction, and finally do some kind of planification or preparation for future mitigation strategies that can be applied in other situations. So specifically in the part that we want to focus here is more on the DevOps, on DevSecOps, if you like, operation. Here we can see a little bit like a flow associated with the approach that we are already defining as, or we already have defined as part of the architecture, and now we are demonstrating, as you see at the end, on different use case, where basically the main idea is that we should be able to support, and here, although you can see different boxes, and some of them, these are there are sub-components that you can have on a certain GUI. It's not that we generate all these GUI, but that they can aggregate. They are functional components of this GUI. So basically, you can we should be able to provide several information. Some of them is how to facilitate that the user, in this case the one that is going to provide or request a certain service of the infrastructure, how to specify either the security aspect or requirements that the service will have. But also how the privacy aspect that need to be taken into account associated to the deployment in that sense. Additionally, we can have solution, or we have some solution that also facilitate that if we are talking about a security administrator, also to be able to specify certain kind of policies that already should be taken into account in order to manage possible situation or mitigation scenario that should be applied in case of on certain circumstances. And obviously, at the end, what we want is to be able to provide an intent-based, I would say, specification. As you will see later, we are using different standards and specification for doing that, so that at the end, the combination of the different aspects that we are trying to provide, mitigation policies, privacy requirement, security, security needs, etc., they can be finally integrated on a intent-based model that should be the one fitted at the end to this security intent-based security management. That is the initial piece that will be in charge of describing in a high level language the main specification of what it will be required to be enforced. And that later can be managed and used by the other component, for example, either for the future analysis and mitigation strategy, but also for the security orchestrator to take that into account, and based on this, being able to translate what it is being required to the different domains, as you can see here, where it's going to be applied. For that, for example, you will see later, we have a mechanism to do several layers of translation of the policies, so that we go from the high level to the medium level to the low level, that are finally implies basically the configuration or the applying of certain command of either through CLI or through NetOps or whatever in the final elements that you can have on the concrete infrastructure that we are using in that sense. So basically at the end, this is the problem, so the issue. So at the end, the important thing here is that, as you can see, the flow is to go from a specification to intent, from intent to more practical I was at the definition of what should be the orchestration. And when we go to each of the domain, basically the application of that orchestration policies to the concrete and the security policies to the concrete resources that are available on that concrete domain in that sense. So for doing that and for being able to manage, here we have specified different, I would say, specifications that we are using in order to do the mapping and to take into account the different aspects that we are mentioning. For example, we are highly involved on the specification that is happening on the Etsy ISC about OpenSlice, where basically they are using the mostly TM forum documentation or specifications to define either the security and the privacy requirement. In that way, that can be used in the way to provide and to fit basically from the first level all the necessary information that should be managed for the orchestration. But also, for example, we are using other specification like the one coming from the network exposure function, the NF, in order to specify and to do the mapping in that sense about what is being required from the point of view of the user and what is being available from the perspective of the infrastructure, so that at the end the policy and the orchestrator should be able to do the mapping in that sense. Similar, for example, you will see later, in order to go to a concrete instantiation for certain policy, for example, we are using extension of the OpenFlow so that we can provide some programmability capabilities of the deployment that we can have at the network layer in that sense. And finally, in order to recover and collect information that later will be used in that sense for the analysis of certain enablers that could be deployed for doing as already presented by Jorge, for doing some kind of analysis of the behavior, for example. Then we are using also, or we are taking into account the specification of the NWDAF. So at the end, we can have a way to collect data, but also to enforce some kind of algorithm based on AI/ML, so that we can do the analysis of the data, and based on this provide the final information for the definition of the mitigation. Indeed, you will see on the next in the next presentation from our colleague from FBI, you will see something quite aligned with this work that we are doing also in the context of another project specifically. Okay, so as I already said, the most important part is the initial, I would say, or what is more focused to the user, if you like, is what we call the human-centric privacy and security aware onboarding specification that I already said is basically a policy driving, taking into account the specification aligned with the TM forum, in that sense that, as already mentioned, are connected to the work that is already standardized on the OpenSlice, in that sense, and basically that provide the northbound to enrich the orchestration for the different layers. Here we are talking first, as you have seen, on what we call the security orchestrator, that they basically provide the end-to-end vision of what security will be necessary to be deployed globally at the high level, and then we apply, or we provide mechanisms to translate this specification, this policy to each of the different orchestrators that could happen at the different domains, depending on their correct implementation in that sense. Also, they can be integrated perfectly between the specification and finally the enforcement that is happening at the northbound, at the southbound. In that sense. Additionally, part of this this work that we have carried out is what we call associate some specification of a privacy quantifier that is also being used later to try to evaluate certain requirements on the privacy that should be applied or should be happening at the level of the service layer, so that we can evaluate whether the privacy is being already compliant or not with the initial specification in that sense. So that provide, in some sense, that we have not support only to the SecOps, if you like, but also to the PriveOps, if you like, so that we can monitor and provide from the specification up to the monitor and evaluation of the operation at the infrastructure level of the different components that are being required to be deployed for the network service. As I said, at the end, the model, as you can see here, is a little bit as a high-level example about basically what we have the different components from the service composition that is being provided for the user in that sense, to the definition of the quantifiers if we're talking about the privacy, and then the interaction with the TMF specification, so that at the end we are able to translate basically all the definition, either from privacy, security, but also about the onboarding that is happening here to the intent-based security component that will provide basically the high-level detail of how all these recommendation and specification are being integrated and being mapped to the concrete possible enforcement that is going to happen at the end-to-end in that sense. In the issue. For the mapping, as you will see later, we have different mappings that are happening depending on different policies, on different also orchestrators. So at the end, what we are providing is a flexible way so that we are not tied to one specific orchestrator, but basically, as I said, try to work with different versions of different models so that we can support the scenario of a multi-stakeholder, multi-domain scenario. For doing this translation of the policy, I think one important thing is that is what this AI-driven policy security orchestrator is, as already mentioned, is that we go from the specification that we just mentioned, where we provide all the requirement, and then we create this end-to-end policy that specify what will be required over the end-to-end service provision, and this specification is later being forward, as you can see here, to the different domains, being the edge, the core, the transport, either from different operators, so that they can take that specification and they can do a local mapping of this specification through their security orchestrator to the concrete collection of enforcement point that they already have. The main idea is that we are not, as I already said, we are not tied to concrete implementation, but every domain will have his own, I would say, mapping or local mapping of collection of resources that they are able to manage, of collection of enablers that they are able to provide, and basically there will be a mapping that is being carried out between what globally is being specified in a high level, in this high level language, to the local level specification that it is do the mapping to the concrete resources that are available on that specific domain. So that's why we have this specification of the policy manager that do the translation, look for about the data service and the enablers that are already available, and do the final mapping so that this mapping can be enforced later to the concrete devices and elements that you have on the final infrastructure in that sense. So in that way, we go, as you can see here, from the specification that is being provided by the user through a high-level detail to a concrete policy that is defined at the end-to-end, and finally a local policy that is applied for each of the different domains through different, I would say, translation as specified here. No? In this process of the security orchestration and policies, we can have different kind of policies. It's not only just to define a policy for filtering or for doing and ciphering end-to-end, but also, for example, we should be able to we are able to provide policies, as already was presented by Jorge, to indicate that certain kind of enabler for doing, for example, a federated learning on a certain component on the infrastructure should be deployed if that BNF exists, so that it should execute and receive data coming from a certain component that is being defined on that architecture. Other policies could be to create for example, a firewall that is going to be deployed, or for example, as you will see later, to launch a certain monitoring that should happen on a part of the infrastructure, so that we can start collecting data, so that later we can learn and apply AI/ML algorithms over it in order to finally create a decision over certain actions or certain situation that is happening there. Okay, so that's mapping. It is shown here that can at the end can go to in a certain domain. For example, it can go at very low level. So at the end, we can translate this with the collection of actions that are going to be enforced at the network layer over the different elements of the infrastructure that is going to be used during the connectivity. So at the RAN, at the edge, at the core, in that sense, and using certain specific mapping to concrete technologies that are applying there. No, for example, just to create an IPsec tunnel that is going to happen end to end between the two nodes that are part of the communication. In that sense, so it's just to show you that in that way we are going through the different, I was at the levels of the hierarchy of the mapping up to the low level. Another important thing, as already said, is that part of this policy, either for the privacy or for the security, could imply the deployment of certain monitoring components. Here you can see an example that we are working, for example, in order to identify a certain situation of anomaly on a network function. In that sense, so to monitor what is happening, for example, the increase on the use of resource of a certain network function. So to collect the information. In this case, that information could be then collected in an infrastructure like a Prometheus, and based on this, we can make an analysis, and based on this analysis, we can decide, based on a certain trust level, whether there is a kind of situation that should be mitigated, and that's required to request to the security orchestrator to take a decision about that situation. This should be driven by the specification being provided by the user, or in some case could be a proactive part that is being defined by the security administrator that complement basically what the user already has indicated about their requirements. So we can combine, in that sense, different policies that can be coming from users or from the security administrator of the entity. All these scenarios already mentioned, actually, we are mostly reaching the end of the project. Now the infrastructure, the enablers that I already showed you, and the evaluation already have been carried out of all the behavior working all together. And now we are applying this solution to to three main use cases that we have defined in the context of the project. And the final part of the project that will happen after this summer period, we will mostly to focalize on applying the architecture over the three use cases in order to obtain performance, evaluate, and all these aspects that you know in that sense. One of them is about protection of 6G infrastructure. So it is for a service provider that is able to have his own infrastructure, and he wants to protect about possible cyber threats that could happen either at the data plane or at the control plane. For example, that's why also mentioned Jorge that we are working with different data sets in order to identify the situation. Another one is linked to the energy sector. So basically how to protect. And for example, now, as you have known that we have this blackout in Spain, it seems not to be by a cybersecurity attack, but basically it could be a typical example of a scenario where you need to identify possible threats and try to do a mitigation action. And finally, a third one is about a smart city platform, and specifically focus on the emergency situation, how to give support to the first responder on a critical scenario in the city. I think something also I was quite relevant to what happened in Spain on Monday. I was in that sense. Okay, so basically as a conclusion, we can say that Rigorous will investigate basically, as already said, on this on how to provide end user or how to translate end user requirement to an intent-based security policy management, and how it should be enforced and deployed first and later to be enforced, to provide this scenario for zero trust and smart security management, provide the solution over end-to-end, and how also to use AI-driven, as already was presented on the previous presentation, that can help on the definition, identification, response, and mitigation of the adverse scenario, and the finally validation of these different use case. And that's all from my side. Again, similar to what Jorge said, if you have more information or you are interested, either contact us. Also, you can go to our website where you can see the last results that we are generating in this month. Thanks.
Thank you, Antonio. Questions from the audience? So while we're waiting to see if anyone will ask, I'm wondering about how you can apply this concept if you have let's say now you have one scenario, but networks are constantly changing and reconfiguring, and staying compliant in real time is a big challenge. So how your approach ensure that policies and compliance are continuously enforced as everything evolves?
Basically, what we have is, we didn't measure that part, but basically, when we are creating the policy is quite aligned with the information that we are at the same time collecting what we call the system model. So basically, system model try to have a continuously update of the information about topology, enablers, component, entities that are being deployed on the different infrastructure element in that sense. So at the end, the main idea is that obviously when you take a certain moment, you do a translation. The translation is being done taking into account what is in this moment available, I would say, on the system model. But the idea is that if the system change and there's a new update or new component or either a change, for example, on the condition of certain nodes that are part of the infrastructure, this is being continuously updated on the system model, so that the orchestrator is able to understand, for example, if need to do a change or mitigation or something like that, because, for example, there's a trigger that indicate that there is a situation that already have changed of the infrastructure, it can be reconfigure the policy or consider another kind of policy or change some parameters of the policy so that they can enforce it again. For example, think about the scenario of having some kind of loading of certain service from one node to the other. No? So we already have in the architecture, I would say, the mechanism to continuously try to monitor the situation of the infrastructure, as I already said, of the enablers and the component, and based on this, they try to trigger, if necessary, because this is like an abnormal behavior, but a normal behavior could be because there is an infrastructure issue, no? Not because of a threat necessary in most of the case. And using that, take into account a new policy that try to do a change on the configuration or a movement of certain component from one infrastructure to another, and this kind of stuff. So this is basically the way where we try to maintain the information up to date and use that information in order to react. That's why we have two kind of policies, what we call reactive and proactive. In that sense, so proactive is more, something more linked by the user intent, if you like. While the reactive is more about reacting to a situation, a change in the condition that could be a threat, could be a change on the configuration, could be another situation that need to be taken into account.
Okay, this sounds well thought through, and sounds like a great project. Thank you very much, Antonio.
Yep, thanks to you and to the audience to be here.
Yes, and in these late hours, if you can say that. So we have two more presentations to go, and the next one is from 6G Clouds. It's from Anastasios, Giannopoulos, and Sotirios Spantideas, and the presentation comes basically from, as said, AI-driven self-healing edge cloud, which is a full meaning of 6G Cloud acronym. And the researchers, Anastasios and Sotirios, are coming from 4.Infinity company. So I will give now floor to them for this presentation.
Hello everyone. Hello, Nineta. Can you hear me?
Yes.
Okay, perfect. And so can you also see my screen in full mode?
Yeah, it's working.
Okay, perfect. So thank you very much also for the invitation. on this webinar. So I will start by presenting a little bit our scenario that we have developed in a framework of 6D Cloud project. So I will present a framework that is named sorry about that. I will present a framework that is named 60. Sorry, I cannot see. Just give me a second. Sorry about that. Yeah. So I will present a framework that is named the AI-driven self-healing for energy-efficient dynamic server activation or deactivation. And the plan here in the 6D Cloud project is to highlight the collaborative interactions among different 6D Cloud frameworks. So what we say as MOF is the management and orchestration framework. And we also have a cloud continuum framework that we call CCF. And finally, we have the artificial intelligence and machine learning framework, IMLF, that provides the AI and ML services. So what you'll see here in this presentation, the architecture, workflows, all the results are the outcome of a joint effort by For.Infinity and also University of Murcia, both partners of 6D Cloud Consortium. Basically, what we'll cover in this presentation is like first, I will start by outlining the general goals of this presented scenario, presenting also a high-level overview of the end-to-end resource allocation loop. Then I will go a little bit through the role of the involved components from the 6D Cloud architecture before going to a step-by-step description of the architectural workflow. Finally, I will jump into the decision-making methods a little bit and present some of the results before concluding the presentation with the feature work that is for the upcoming period in the project. So basically, the main objectives of the presentation and the motivation behind this work, as are shown in this slide here. So the first main motivation is to enable synergies among the three frameworks, the management orchestration, the cloud continuum, and the AI/MLF framework for providing self-configurable and automatic resource scaling. Moreover, we also propose a general purpose control loop for AI-driven cloud continuum optimization under different SLA policies and also considering dynamic compute traffic. And finally, we also evaluate the impact of machine learning on the performance of the cloud continuum framework, considering also the energy efficiency in managing compute servers for network services. So basically, the key features that you can see here that are demonstrated here in this work are the practical integration of the model training and real-time model inference of an LSTM model for forecasting the CPU utilization. And also we demonstrate the SLA-driven orchestration and how this is enforced in the network service. We also present the AI-assisted resource management with the 6D Cloud architecture. And finally, we also emphasize the optimization of the CCF resources for energy efficiency and adaptability, aligning also with the self-healing cloud edge computing principles and also the zero-touch concept that is introduced for the 6D networks. Okay, so basically, this slide shows here a high-level view of the proposed approach of the development methodology, let me say. So we propose an end-to-end resource allocation loop that integrates the cloud continuum. You can see are the building blocks that are colored blue. The management orchestration framework, it's the green one, and also the IMLF framework. So this is the red one. We demonstrate how this end-to-end resource allocation loop, continuous loop, can be implemented to manage cloud and edge resources for different network services. So first of all, we have the monitoring of the dynamic traffic data. So we collect the real-time metrics such as the CPU utilization or the energy consumption. So these metrics are time varying based on fluctuating user traffic. And then, moreover, we use all this data to train an AI ML model in order to predict the future resource usage. And we also continue in the loop. We also use the anomaly detection module in order to identify potential SLA violation or possible network anomalies based on the predictions and policy-based thresholds. And finally, we apply some corrective actions on the infrastructure, dynamically adjusting compute resources through self-healing mechanisms. Okay, so this is the overall architecture of the 6G cloud. Okay, it's not refined yet, but it will be in the upcoming period. But here you can see the three main frameworks. So we have the IML framework, and we also have the management orchestration framework. And here below we have the cloud continuum framework. And all these frameworks support the deployment and running of a network service. So let me first describe a little bit the role of the key components that are engaged in this proposed loop. So in the CCF level, we have, first of all, we have the resource database, which is the component that collects real-time metrics, including energy consumption, resource utilization, and so on, as well as workload distributions from the cloud and net servers. And then we also have here the resource orchestrator, which is the building block that is responsible for allocating the resources dynamically to network services, and also enforces the reconfiguration based on AI/ML model outputs. And finally, in the CCF, we have the autonomic CCF operations. This is a component that is considered to host all the training or inference module that are provided by the IML framework. So this can be done using historical or for training services or real-time data for inference purposes. All this data come from the resource partitions. Regarding now the IML building blocks, we have the learning module, which actually trains or continuously refines prediction models using historical new data from the CCF. And we also have a repo, a model repo, so a models database, which actually stores the trained models that are ready for deployment. And finally, in this scenario, we also consider the performance monitoring module, which actually monitors the accuracy of the deployed LSTM models during their inference. So to evaluate the performance of the running models, more or less. And finally, in the MOF level, we have two main building blocks that participate in the scenario. So we have a global OSS, which actually provides policy-based configurations for service availability or energy efficiency, and also interacts with external stakeholders. And we also have the service orchestrator. That's the component that orchestrates the network service deployment, as well as is responsible for SLA policy enforcement by identifying threshold exceedance, interfaces with the CCF also to ensure resource reliability. And inside this service orchestrator module, we also consider an anomaly detection sub-module, which actually its role is to detect workload anomalies based on thresholds or predictive outputs from the machine learning models. Okay, here in this slide, okay, I have more or less tried to summarize a little bit what the network service is for the 6G cloud and the 6G cloud architecture. And in general, we consider that the network service can be composed of several run network functions or virtual network functions, and also some core virtual network functions, so forming a service function chain, as you can see here. So these functions, these VNFs, may run on a single server, for instance, in case of small scale or isolated network services, or can run across multiple servers. So we have the single server and NS deployment. We also have the multiple server and NS deployment in cases of high capacity network services where VNFs are distributed or may be distributed across edge, far edge, or cloud resources. So we maybe have different VNFs running at the same time, different in infrastructure. So far-edge servers or cloud servers. So all this architecture for the network service allows us to monitor some metrics of each deployed VNF directly on the server, edge, or cloud that is located. For instance, as I mentioned, CPU utilization or consumed power during the VNF execution deployment. Moreover, also we can this monitoring process enables us this VNF concept allows us also to migrate VNFs to different servers, especially when strict SLA limits are required by the network service. For instance, if strict latency requirements are required from the network service, then we need to move the VNFs closer to the user in the far-edge servers. Or, for instance, we can consider some power consumption requirements, and we want to minimize the overall power consumption of the VNFs of the service chain. Okay, and now here I will try to go step by step. Here, this is the overall architectural view of the considered scenario. Starting from the bottom of the figure, you can see the physical infrastructure layer that includes the UEs and IoT devices served by radio units, as well as the edge and cloud servers that host the VNFs of a deployed network service. So we have two kinds of resources. We have resources marked in green. So we assume that constitute a resource partition for a single network service, NS1, for instance, whereas we have a resource partition colored red that constitute a different network service. And also, if you look here closely in the infrastructure, we also have deployed a monitoring agent, or MA software component, in its edge cloud server. So this monitoring agent collects time series metrics from the infrastructure. So above this, we have the CCF layer that manages the physical infrastructure through the resource orchestrator component. And also, as you can see here, we have the IMLF blocks for the scenarios. And all these blocks, the ML model, the learning module, the performance monitoring module, and so on, are overlaid inside the autonomic CCF operations, which means that I directly deployed in the CCF. Finally, at the top, we have the management orchestration layer that includes the modules responsible for the orchestration of the overall network service, as well as the SLA policy enforcement. So this latter service orchestrator includes also the identification of server overload to notify the resource orchestrator for further scaling corrections. So if we go step by step here in this scenario, in step 0, we set any service level threshold associated with the overall energy or CPU consumption through the OSS. Then the first step is to collect data from the resource partition through monitoring agents. Different monitoring agents can also be used here, software agents. So the collected data are then stored in the CCF resource database. Following the process, the following step, we have the time series historical data that are utilized to train offline and machine learning model in order to provide forecast of the total CPU utilization of resource partition 1, so the green resource partition here. And the following step here is that this model is deployed and used for inference using the real-time samples from the resource database, and the predictions are sent to the resource orchestrator inside the MOF. Inside the MOF, as I already mentioned, we have also the anomaly detection module, and that analyzes these predictions by the machine learning model and targets to identify resource partitions with potential CPU overload. And when we forecast an actual CPU overload, so the anomaly detector notifies, triggers an alert to the resource orchestrator of to the action taker that resides actually in the resource orchestrator, And this action taker is responsible for performing a corrective action to counterbalance this CPU overload, the SLA violation. So among many options here, we use dynamic scaling of the NRS resources as a corrective actions, but different also corrective actions could be applied. So here we scale up or scale down the resources, either by activating new servers or deactivating the underutilized ones. And moreover, we have the performance monitoring tools inside the autonomic CCF operations that are responsible for comparing the predicted, the forecasted, and the actual values of the CPU usage. And upon detection of model performance degradation, this component is responsible for initiating retraining process and invoking more or less the learning module again with more recent data. And finally, the updated resource metric reports are continuously gathered in the resource database and can be used by the machine learning model for periodical training. Now here I will show a little bit of the demos that we have prepared. So after the deployment of a Kubernetes-based environment, we use Prometheus exporters, Grafana, and Kepler tools. All these tools can be used as monitoring agents to monitor the CPU usage or the power consumption of the server. So we are able to collect here, as you can see, several resource metrics in real time, all associated with the VNFs running on top of the resource partition. So basically, these VNFs are part of the network services. So here you can see the real-time tracking of the power consumption corresponding to an underlying Kubernetes microservice. So using this monitoring engine framework, CCF, the cloud continuum framework, is capable of collecting live data from the running network services for further usage by the AI machine learning module. Regarding the model training, we use now this data based on the PyTorch and the Python and Kubeflow and also in the Kubernetes environment. So we use a subset or all of these tools along with different ML ops platform in order to implement a LSTM, long short-term memory network that predicts the upcoming CPU utilization based on the historical data of CPU utilization values. So here we present the environment. We run actually the code. It's the training process, and you can also visualize here the real-time course of the training, indicated the gradual loss decrease as the number of training steps or epochs increases. Okay, so once this training process is stabilized or converges, the trained model is finally stored in the model's database and becomes available for future deployment and real-time inference. So for the model inference and the performance monitoring, the trained model is deployed in the autonomic CCF operation, as I mentioned, and real-time samples are gathered and are provided to the model input, to the LSTM model input, for inference, as you can see here. So the model is served using model serving modules, and the inference mechanism, okay, we use here PyTorch libraries. So indicatively, the trained model has been trained for CPU time series data corresponding to real-world traffic traces collected from the Torino streets. So this is the data that you see here, and this data have been provided over several months training data. As you can see, there are certain CPU usage spikes indicating that we have or may have SLA violation depending on the selected policy that requires detection and resolution. So periodically in time, you can see we have also performance monitoring tools that are used to evaluate the prediction accuracy, and this can be done by using the real predicted CPU usage values, for instance, to produce metrics, for instance, as the mean absolute error or mean squared error, and so on. in this scenario, up to this work, we have selected 3 indicative methods for detecting anomalies. And so we include one reactive method, which actually does not use ML predictions for activating a new server. And we also use a proactive ML-based method. So we use the predictions and forecasting of the LSTM in order to, and we set also a fixed threshold. So we use the model inference to estimate the upcoming anomalies. And finally, we use also a proactive method with adaptive threshold. So we use here also the LSTM forecasting capabilities with a different kind of threshold, not a fixed threshold, but an adaptive threshold to ensure lower sensitivity to traffic spikes and allow for more conservative server actions. So here also you should know, I should mention that this is just demonstration of some indicative anomaly detection methods. And by using this developed framework, a user can also program different policies. So basically, for the implementation here of these anomaly detection methods, here you can see different labeling of traffic time points as normal or as anomaly, with the anomaly being raised when the threshold values are disrespected and reflecting alarm situation for further corrective action. So once the alarms are triggered, we compare the different anomaly detection methods, and here you can see some results indicating that the adaptive threshold policy results in the lowest number of active servers, since it dynamically adjusts the threshold based on the current traffic pattern, while also providing significant energy savings. So here you can see that the mean power in the right figure, you can see that the mean power consumption is using the adaptive threshold policy achieves significant power savings as it maintains a lower number of active servers. As a future work, we have several key directions about that. So first of all, we can implement this into a large scale, this system, and also perform real world validation. So the plan in the upcoming period of the 60 Cloud project is to deploy this AI-driven self-healing system at a larger scale, testing also in real world networking environments, with multiple also operators, since what I already demonstrated reflects the use of one network service. So this, by implementing the system at large scale, will help us evaluate its performance under diverse and dynamic network conditions. So moreover, we plan to use some advanced learning on the optimization techniques. So we plan to explore federated learning in order to train models between different network services without sharing any of the underlying data. And we also plan to use transfer learning to enable decentralized AI across different network environments. And finally, we plan to expand the corrective action mechanisms. So instead of reacting to anomalies, when the system to proactively redistribute the workloads based on AI-driven predictions of future demand. And also this corrective action mechanism will allow for a smoother load balancing and reduce the need for drastic corrective actions. That's all I have. Thank you very much for your attention, and I'm here to answer any possible questions. Thank you. You can also follow the 60 Cloud project and find us on LinkedIn and online. Thanks.
Thank you, Sotirios. So I just wanted to ask, since the SLA are very important, and when you speak with different telecommunication operators, they are mostly governing things through the SLA. So if it's not in SLA, sometimes they don't care much. And I'm wondering for the SLA policies, for how you define it. So definition influence on the orchestration workloads in your system. How did you work with the SLA?
Okay, thank you for this question. So first of all, for the SLAs, for now we have done some very indicative examples for simple SLA policies for simple network services, of course, but it is quite general because in this framework, a user or a network service provider can log in through the portal through the OSS and actually program his own SLA. So basically, if you have a network service that requires, strict latency, includes strict latency requirements, or has like broadband requirements, for instance, then or resilience or reliability requirements, then this can be configured by the user, and it will be also taken into consideration during the thresholding, the anomaly detection of the threshold policy.
Okay, thank you.
Okay, thank you very much. Is there any other question?
In the chat, there are no visible questions. So if no other people raising hands or unmuting themselves, I think we can go for the next speaker.
Okay, thank you very much.
Thank you again very much, guys, for the presentation. And thank you all for sticking with us to the very end. We are a bit behind the schedule, but the last presentation, I think it's very interesting, and everyone who stayed to the very end, I think they're going to see this and will benefit basically from hearing from Merlijn that comes from IMEC, and the presentation is about using WebAssembly to create resilient cybersecurity devices. And Merlijn, beside IMEC, has a position at the University Ghent in Belgium. He leads the research in number of domains, mostly focused on software deployment and trust in cloud and on devices. And this WebAssembly is a very hot topic. There is a lot of current research, but we can hear more from his side directly. So Merlijn, I will give the floor now to you.
Hi, thank you, Nineta. Can you hear me well?
Yes.
Okay, so I had the introduction, so I'll go immediately do the presentation itself. This research is basically about the challenge of software updates on IoT devices and the challenge of software supply chain security on IoT devices. To give you an example, the average lifespan of a car in Europe is 18 years, which means that most cars, or at least the majority of cars, survive for at least 18 years after they have been put onto the market. If we look back 18 years ago, the pinnacle of engineering was Windows XP. But for some reason, a lot of people didn't really like, Windows Vista, but a lot of people didn't really like Windows Vista. So 18 years ago, most people were still booting up to this beautiful screen. The memories are coming back. But the problem is that these cars, even 18-year-old cars, they have software. They are running software. They are running software in security critical applications. How do you keep updating software on a car that was initially compiled and developed on Windows XP? Well, the answer is incredibly slowly. A lot of cars are running with software packages that are over 10 years old. OpenSSL, for example, is a critical piece of software to secure communication between a car and external devices and Bluetooth and things like that. If OpenSSL in your car is 10 years old, then basically your car is vulnerable to a lot of attacks. And we are also seeing this if we are looking into common CVEs in terms of automotive. Each year, these are rising a lot. It's so bad that on TikTok, kids are even sharing with each other how to hack into very common cars, and they see in the US there is an incredible increase in car thefts. In Europe there is a smaller increase in car thefts because we have stricter security guidelines for cars, but still over 60% of all breaches of software happen because the software is outdated. So what I mean with this is that over 60% of breaches happen using a vulnerability in software that was known, that there was a patch for to patch that software, and that patch was released by the manufacturer. So if everybody would update all their software all the time immediately, we would immediately cut back on 60% of cyber vulnerabilities, on cyber breaches. Interestingly, though, this problem of how do you always get the latest software to customers, we've actually already solved this in browsers. And so, believe it or not, I am going to try to convince you that you should put a browser in even the smallest of your IoT devices in order to solve this. One of the great developments of browser technology over the last few years has been WebAssembly. Initially built as a technology in order to distribute very beefy, resource-intensive applications using web browsers. Now it's also used in IoT devices. It's also used in a lot of applications. If you look at Adobe Creative Cloud, if you look at basically any streaming application, these are all built on WebAssembly in order to make it possible and to make it very, very easy for a software vendor to target over thousands of devices. Amazon targets over 9,000 different device types with a single WebAssembly compiled application. And I say we need to go even further. We need to use WebAssembly and the WebAssembly system interface for embedded. Because first of all, WebAssembly gives you binary device portability. So with the rise of ARM systems, with the rise of RISC-V systems, this means that it doesn't really matter where your logic is running. You have a single application package, and that can run on any device. It supports, compared to traditional embedded development environments, it supports much more programming languages and wide language interoperability. So for embedded devices, most embedded developers are still using C. And this is not because they really love C. This is because this is simply how it works. You buy a certain chip and you get from the manufacturer of that chip, you get a C compiler. Often a C compiler that's either proprietary or that's a hard fork of an open source C compiler. And so you can only compile and deploy C to these chips. WebAssembly allows you to use basically any language that you can compile to WebAssembly. It also gives you forward compatibility with newer application toolchains over multiple decades. So I've talked about Windows XP. Literally, there are a lot of companies that have a Windows XP virtual machine running somewhere in order to compile security updates for some of the embedded devices that they have. With WebAssembly, you can just use the latest toolchain, the latest compilers on the latest operating system to compile your application to a device that is 15, 20, 30 years old. And then finally, and this is the most interesting from the standpoint of my background in cloud computing, sandboxing, virtualization, WebAssembly gives you a sandboxing technology that is more secure than Linux containers, but so small that it can fit on devices down to 268 kilobytes of RAM. So you can run your application as isolated parts on these truly tiny microcontrollers. But very importantly, WebAssembly still ensures that you can take your existing software that you wrote in C for your microcontroller, recompile it to WebAssembly, and then still run it in WebAssembly. You don't need to rewrite your existing software. And secondly, You get near native efficiency in execution and in compilation, which is incredibly important on these low resource device types. Even though WebAssembly sounds as like it's a very resource heavy technology, this is not actually the case. WebAssembly is custom built to be incredibly highly performant. So we are building, as part of the Elastic project, we are building what we call cyber physical WebAssembly. WebAssembly specifically built for IoT devices. For example, we have a prototype where we use WebAssembly for device drivers. The idea is that every single device driver in your operating system is now running in its own sandbox. So when there is a supply chain vulnerability in that driver, it will only affect the system that that driver needs to have access to, and the rest of your system is still secure. This is very, very beneficial for the security aspect, but also in terms of reliability. If your device driver crashes, the rest of your device logic is still running. And then secondly, portability. If you have a device that's 10 years old, 20 years old, and maybe the screen breaks in that device, you want to plug in a new screen. They don't make the old screens anymore. Well, with WebAssembly device drivers, it's not an issue. You don't need to reflash those devices. You don't need to update your kernel. You just need to load a different WebAssembly module with the latest driver for that latest piece of hardware. We have a very cool demo that we will also show at EU CNC, I think is a conference called, where we basically run Pac-Man, the Pac-Man game, together with a USB device driver for an Xbox controller as WebAssembly modules inside of a WebAssembly runtime. We have this stuff working on Linux, we have this stuff working on Windows, and it also works on microcontrollers with real-time operating systems. And the device driver itself, if you want to use a different external USB device, if you want to use a different controller, well, that's not an issue. You just plug in a different driver compiled to WebAssembly. We have a preprint available for this. It has been accepted to IEEE norms, and the preprint basically shows that in terms of latency overhead, the latency overhead is incredibly small. So small that you can basically ignore it. This overhead is smaller than basically the round trip time of a USB packet. And so because of that, it doesn't really matter whether your application is running natively or whether your device driver is running natively or whether it's running in WebAssembly. Same with the throughput. Throughput is not really changed by running your workload in WebAssembly. The main downside in terms of resource usage, the main downside is that your application will use significantly more RAM than if it was not running inside of WebAssembly. But this is something that a lot of very smart people are working on trying to improve. And so maybe in a few months, maybe in a year, we will also be able to show that memory overhead is also small or smaller. In order to make this possible, and not only for USB devices, but also for things like CAN buses or GPIO devices or I2C devices, we are building a whole bunch of standards. Because let's go back to the example, we're talking about making it possible for devices to be updated in 20 years, in 30 years, and 40 years. If we want to do that, we have to have standards. So we're working with the W3C in order to create official standards for these APIs so that they can be adopted in compiler toolchains, they can be adopted in standard libraries, and be used in order to improve the security and update ecosystem for these devices. And we also have a whole bunch of implementations, which are right now proof of concepts, but we're working on making these more production ready. This was basically what I wanted to talk about. I have to put out huge thanks to a lot of people, including the Bytecode Alliance and the W3C WebAssembly System Interface subgroup, who are generously hosting our work, supporting our work. So that's it. If there are any questions, I'm happy to answer them.
Yes, I'm also happy to hear if there is any question from the audience. Okay, about the WebAssembly, I would like also to ask some question because of the maturity of the actual ecosystem, and as someone working in this for some time, I would like to ask you, how do you see the forward compatibility and what developers could expect in near future?
Yeah, so in terms of forwards compatibility, I have to note that these standards that we are developing, these standards are still not officially set in stone yet. So there is a possibility that the standards that our prototypes use right now, that these standards can still change before they mature. For some of the standards, we expect them to mature in this year, but for some of the standards, we expect them to only mature in 2026. However, if you want to use these interfaces inside of real-world products, what I think is very interesting to know is that the Bytecode Alliance is actually working on an LTS release for a WebAssembly runtime that includes a first version of these standards that will be supported for a very, very long time. This is work in collaboration with Siemens, Sony, a bunch of other companies that are all committing, because they want to also integrate it in their products, that are all committing to support this runtime for a very long time and also support them in compiler tool chains. And so once this LTS release comes out, this is something that I can definitely recommend companies to include in their products, because that will be support for a long time. Specifically, the runtime that I'm talking about is WAMR, W-A-M-R, the WebAssembly Micro Runtime. This will release an LTS release quite soon.
Perfect. This sounds really amazing. I mean, the effort put into the working group and in the project itself, I think this really can change some things, and it could be a game changer in future for a lot of things. Beside this, can you also tell me about how do you see, I mean, the main differences if you compare WebAssembly to a specific implementation, let's say compared to the Java virtual machine, how you see the benefits, what comes from the WebAssembly that doesn't comes with JVM?
Yeah, so it's a common question, because like maybe 10, 15 years ago, the JVM was really being pushed as basically very similar use cases. The idea of write once or run anywhere, architecture independent bytecode. Some products still use the JVM on microcontrollers. Some products were using the JVM inside of the web browser, but the JVM failed in many of these fields. And WebAssembly, basically from its inception, really tried to learn from the 20 plus years of JVM experience. One of the advantages of WebAssembly is that it's standardized as a compilation target for any language, while the JVM is very much tied to Java and how Java works. And so it's very, very difficult to compile other programming languages to the JVM. WebAssembly is also sandboxed by default. And this is a key enabler of both the security and robustness, but also of the truly cross-platform capabilities. Because a big issue with Java applications, the reason why many Java applications are not truly cross-platform, is because they have a tendency to very quickly call into operating system specific APIs, because they can, because they're not sandboxed in any way. However, WebAssembly is sandboxed by default. It has no access to operating system specific APIs, and you can't even enable it in any way. You need to go through the cross-platform WebAssembly specific APIs in order to do anything on the host system. And so because of that, Portability of WebAssembly is basically if it runs inside of WebAssembly, it will run anywhere. And then in terms of security, this is amazing. This is really a technology that is adapted to this current ecosystem of how software is being built. Because in the past, yeah, software was monolithic, a single component from a single vendor, and maybe you have one or two suppliers of libraries. But today, all the software is just composed, a whole bunch of stuff connected to each other from all different kinds of suppliers. And so you really want each component to be individually sandboxed. And because of WebAssembly's very performant sandbox, this is great. This is a great advantage.
Thank you. I think, again, this is a very nice project, and I invite everyone to follow. I'm not sure if there are questions. If no other questions, I think we can close the webinar for today. I think not. Okay, thank you all again. Big thanks to all the speakers and all the participants, especially to presenters for this great presentation and for discussion. So we hope that today's session gave you valuable perspective of how AI-driven security and orchestration can be done through these presentations, use cases, and actual algorithms. We give a bit broader perspective, so we touched base on data sets and processing of these data sets, but also on the network side and also on the other aspects of the security itself that goes beyond the telco industry. So we look forward to continue these events in future. And I hope that you enjoyed today's webinar. Bye. Thank you all again.